Okay. Yeah. A very good evening, all. So in the yesterday's session, we discussed about the SCR dynamic characteristics, right? Let us have some discussion on this numerical. This numerical is from booklet. You can check it. Okay. Okay. So let us first read it. During turn off of a thyristor, idealized voltage and current waveforms are shown in figure. Okay. So here VA and IA, that is the voltage across thyristor and current flowing through the thyristor, they have given waveform VA here, and here it is a IA. Next, for a triggering frequency of 50 Hertz, find the mean power loss due to turn off. Our task is to find the mean power loss. That is nothing but the average power loss. Okay, due to turn off. Also obtain the reverse recovery charge, means QRR we need to find. The same QRR, whatever the expression for the QRR we wrote in the case of diode, the same expression we can use here. Because you can check here IA, after this instant IA is negative now, right? And again it will be decreasing towards the zero. So QRR means what? It is a reverse recovery charge. If you recall the reverse recovery process in a diode, you will understand. Yes, the same curve was there. Okay, but this is for thyristor they have given, right? And this curve we have discussed in the yesterday's session, right? Now here the QRR means what? It is like a area under this triangle, right? So can we write QRR is equal to area under the triangle is equal to 1/2 into 300, right? This length, this height is 300, and into what? This total length from here to here, whatever the length will be there. In this way we can find the QRR. So let me first write the QRR, reverse recovery charge. Reverse recovery charge, QRR, is equal to area under the triangle, right? So it is a 1/2 into 4 into 10 to the power minus 6, right? This full is 4 plus 2, that is a 6 microsecond. So it is a 6 into 10 to the power minus 6. So that's why it is a, sorry, 6 into 10 to the power minus 6 we need to write. Instead of 4, there should be the 6, right? So this is 6 into 10 to the power minus 6, right? Into this height, it is a 300. So into 300. So if you check, it is equal to 3 into 3. So that will be 900 microcoulomb, right? 900 microcoulomb. This is a QRR. Is this clear? Reverse recovery charge, QRR. It is a 900 microcoulomb, right? Next, yeah, commutation we will discuss after this numerical, right, Pratik? So now mean power loss due to turn off we need to find. Okay, mean power loss, we know the power loss is equal to frequency into energy loss, right? How to find the energy loss? So for that we need to write the expression for this waveform, expression for this waveform, and the expression for this waveform. Now you can check here, and let me write first power loss or the mean power loss. Mean power loss is equal to switching frequency into energy loss, right? Into energy loss or switching energy loss, you can say energy loss. Okay, energy loss. So how to find the energy loss? Energy loss is equal to V into integration of power, right? That is the V into I, okay, into dt. We need to integrate the power. Now you can check here from this point till this point, right? From here to here you can check. Here the current is non-zero. Current is non-zero. But what about the voltage? You can check this point means on the voltage it will be here on the voltage plot, and this point is nothing but here. Okay, so now you can check corresponding to this 4 microsecond, what is the power loss? That power loss will be zero only, na? That because current is non-zero, but what about the voltage? Voltage is zero. So ultimately, what we need to do? We need to find the power loss only for these 2 microsecond, na? Because here during the 2 microsecond, the product of voltage and current is non-zero. Are you getting the point, right? So we need to find the power loss only, yes, for these 2 microsecond, for these 2 microsecond. Is this clear to all, right? So let me write the expression for this curve and expression for this curve as well. Okay, so we need not to write the expression for this curve now, right? So how to write the expression for this curve? Because whatever till now we have discussed regarding the energy loss, we are having the expression like 1/6 into V into I into that time, na? Okay, but that 1/6 into V into I is applicable only when one is decreasing and second one is increasing. Means either voltage is decreasing, current is increasing, or current is decreasing and voltage is increasing. This type of shape if we are having, then and only then we can write that 1/6 into V into I into the time. But in this case, you can check here current is also, yes, you can check here current from -300 to this 0. Means it is like current is decreasing and voltage is also decreasing, na? So we can't use here the expression whatever we have already derived. Is this clear? So here we need to write the expression for these two curves, and after that we need to simplify for the energy loss, and then we can find the power loss. Is this clear, right? So what will the expression for this curve? Let me write during t1 is equal to 2 microsecond. During t1 is equal to 2 microsecond. During t1 is equal to 2 microsecond. Yes. What is the expression? You can check. This is a increasing, na? Right? From -300 till 0. Okay. What about the slope? Slope is positive or negative? Slope is positive, right? Slope is a positive. So now can we write the expression here? Initially is -300. Initial value is -300. Okay. And then we need to write the slope. What about the slope here? Slope is equal to y by x, change in y divided by change in x. What is the change in y? Change in y is like a 300. What is the change in x? It is like a 2 micro. Okay. So can we write it as, yes, 300. Let me write it as a first it is for IA. Okay. IA is equal to 300 divided by 2 micro, 2 into 10 to the power -6, right? 2 into 10 to the power -6 into t minus 300. Okay, minus 300. You can check here. This expression is valid. This expression is valid only for this t1 interval, that is for 2 microseconds. So as this expression is valid, only for 2 microseconds, so can we say that the t is equal to 0 in this expression? The t is equal to 0 means which point? T is equal to 0 is nothing but, yes, this point indicates the t is equal to 0 for whatever the expression we have written. You can check. Put t is equal to 0, right? Put t is equal to 0 here. So this term will become 0. So it is a 0 minus 300. So it is a minus 300. So you can check the value of IA. It is a minus 300, right? Next, after that, you can check as t increases. T increases means from this point till we are moving towards the 2 microsecond. This instant means from here we are moving toward this point. Okay. So as t increases, what will happen? The value of this term go on increasing. So the difference decreases. So you can check here. From -300, we are reaching towards the 0 value. Again, you can check at t is equal to 2 microsecond. T is equal to 2 microsecond means which point? This point indicates t is equal to 2 microsecond. Okay. So at t is equal to 2 microsecond, it is 2 micro will get cancelled out. So it is plus 300 minus 300. It will be 0. So you are having IA is equal to 0. Is this clear? So whatever the expression, yes, I have written, that expression is, yes, applicable for only this time interval of t1 is equal to 2 microseconds. Similarly, can we write the expression for the VA? Means this curve. Okay, we can write expression for VA. VA is equal to, yes, you can check what is the slope. Slope is a positive only. Okay, slope is positive only, right? So it is like a, we can write change in a y, that is 100 divided by change in a x, that is a 2 micro. So it is 100 divided by 2 into 10 to the power -6 into t minus initial voltage, that is 100, right? So this voltage is 100. Okay, minus 100. So that's why you can check again whatever the expression we have written here, that expression is for this curve. Okay, that expression is for this curve. Is this clear? Sir, how minus 300 came? Okay. Minus 300 is here because you can check na. This curve has started from this instant, and corresponding to this instant, what is the value of current? It is a minus 300 na. So that's why here we need to consider that initial value is nothing but minus 300. Before this, whatever we wrote, okay, at that time we consider that value means suppose you are having the voltage which is changing from plus 600 to the zero na. At that time, what initial voltage we consider it as a plus 600, but in this case it is a negative na. So that's why we need to consider here minus 300. Is this clear to all? Right? Okay, once again I will explain. Right? So here we are having the curve, right? That is a linear. Okay, it is a increasing, so slope is a positive. So this is a slope is positive and it is a linear na. So what is the expression? Y is equal to mx plus c, and that c is nothing but your initial value. So here initial value is minus 300. So that's why I have written here minus 300. And what is the slope? Slope is a change in a y, that is equal to 300. Change in y means what? So yes, y is changing from minus 300 to the zero na. So change in y is like final value minus initial value. Final value is 0. Initial value is minus 300. So 0 minus of minus 300. So it is a 300 only. Okay. So 300 divided by change in the x, that is a 2 micro. Okay. So you can check here 300 upon 2 micro into t minus 300. In the same way, we can write for VA. Now we can find the energy loss. So therefore energy loss. You can write power loss also directly. Doesn't matter. Energy loss is equal to integration from 0 to t1. Okay, integration from 0 to t1. It is a VA into IA into dt. Okay, so it is like integration from 0 to 2 micron, 2 into 10 to the power minus 6, right? 2 into 10 to the power minus 6. What is VA? 100 upon 2 micro, right? So 100 upon 2 into 10 to the power minus 6 into t minus 100 into what is the IA? IA is 300 upon 2 micro into t minus 300, right? Is a minus 300 into dt. Okay, so now we can simplify it. Take 100 and from here, from this bracket take 100 outside, from this bracket take 300 outside. So it is like 100 into 300 na. Okay, into in the bracket we can get it as integration from 0 to 2 into 10 to the power minus 6. Let me use this as a curly bracket. Okay, so we can write it as a t upon 2 into 10 to the power minus 6 minus 1. Okay, into this term will be like a, here it is a t, right? T upon 2 into 10 to the power minus 6 minus 3 minus 1, because 300 were taken outside. Okay, so that should be minus 1 only into dt. Is this clear? I've taken 100 outside, 300 outside. So you can check 100 outside means it is like t upon this term. This minus 1 will be there. So 300 also were taken outside. So t upon this term minus 1 will be there. Okay, so therefore we can write which is equal to 100 into 300. So it is a 300. Yes, you can write it as 30,000. Okay, into, now we can write it as a, yes, integration from 0 to 2 into 10 to the power minus 6 in bracket, that will be like a t square upon 4 into 10 to the power minus 12 na, this term into this term. Okay, so it is like t square upon 4 into 10 to the power minus 12. Okay, next minus t upon yes, this term into this minus 1, right? So that's why it is minus t upon 2 into 10 to the power minus 6, right? Next minus t upon this term, this minus 1 and this term. Okay, so 2 into 10 to the power minus 6 and plus 1 will be there, na? -1, so it is a +1 into dt. Is this clear? I have taken simply multiplication of these two brackets. Okay, so it is equal to 30 into 10 to the power 3 into, we can write it as, so t square upon this term. So what is the integration of t square into dt? So it is a t cube by 3, na? T cube upon 3 into 4 into 10 to the power -12. Okay, limit 0 to 2 into 10 to the power -6. This is the one term minus, this is the same term, na, we are having t minus t minus t. So it is a -2t. So I'm directly writing it as 2 into t square upon 2 into 10 to the power -6. Is this clear? 0 to 2 into 10 to the power -6. You can check. This is minus t upon 2 into 10 to the power -6. This is also minus t upon 2 into 10 to the power -6. So can we write it as -2t upon 2 into 10 to the power -6? So that's why this 2 is here. And integration of that t will be t square by 2. So that's why the denominator 2 I have added. And this term as it is, right? 2 into 10 to the power -6 as it is. Next, plus here it is a t. Integration of 1 is t. 0 to 2 into 10 to the power -6. Now you can check which is equal to 30 into 10 to the power 3 into, we can write it as, yes, this can be written as 2 into 10 to the power -6 cube. So it will be 8 into 10 to the power -18 divided by 12 into 10 to the power -12. This is one term minus 2 into, it is a t square. So 4 into 10 to the power -12 divided by 4 into 10 to the power -6 minus this term 2 into 10 to the power -6, right? 2 into 10 to the power -6. Now we can write it as, which is equal to, yes, here you can check 30 into 10 to the power 3 into, yes, 10 to the power -12, 10 to the power -18. So that will be like a 10 to the power -6 only. Okay, so 8 by 12. 8 by 12, we can write it as 2 by 3 into 10 to the power -6 minus 4 will get cancelled out. So that will be like a 2 into 10 to the power -6 minus 2 into 10 to the power -6, right? So if we simplify it, we'll be getting it as equal to, so 30 into 10 to the power 3 into, yes, this term will be, yes, it is a 3.33 into 10 to the power -6. It checks sign once. Yeah, last let me check once. Yes, it is a plus, no? So that's why here it is plus. Correct. Plus, so this will be a cancel out. Correct. So therefore, we can get it as 2 by 3 into 10 to the power -6, right? So if we simplify it, we'll be getting it as 2 by 3 into 30, right, into 10 to the power -3. Na? So it is a 0.02 joules. Na? Now, what about the power loss? This is energy loss. So therefore, power loss. Switching frequency 50 hertz into 0.02. So it is equal to 1 watt, right? It's equal to 1 watt. Is this clear? Correct? So here, the thing is, the power loss corresponding to this interval, right? 4 microseconds, that will be 0. Okay. So in this way, we can find. Next, let us discuss the next term, next concept. Turn on methods we already completed. Yeah. So before moving towards the commutation, let us discuss the two transistor analogy of SCR. Okay. Basically, the two transistor analogy of SCR is used, or you can say this will give the mathematical proof for the gate triggering of the SCR. In the gate triggering of the SCR or in the turn on methods of the SCR, whatever we have discussed, That was a theoretical approach. Okay. And generally we say that the gate triggering is the most popular method and those things. Okay. And this two transistor analogy will give the mathematical proof for how the small gate current circulation will cause increase in the anode current of the SCR from leakage value to the high value. Okay. So purpose is very clear. Okay. The purpose of the two transistor analogies, it will give the mathematical proof. Okay. For how the anode current of the SCR changes from leakage current to the high value. Okay. By a circulation of small gate current into the gate cathode circuit. Okay. So in order to understand this two transistor analogy of the SCR, here we are having the two transistor. Okay, so transistor word is there. So what we are doing here, SCR is a PN structure we are having, right? PN structure. That structure we have divided. Okay, that structure we have divided as PNP and NPN transistor. Okay, so how we have divided it? Let us discuss. So yes, this is the structure we are having. Let me write it as a P or the P1, right? This is like your N1, this is a P2, and this is a N2, or you can say N1 minus. Okay, anode of the SCR, cathode of the SCR, and here it is a gate of the SCR. The same structure, the same structure. Now we are going to redraw this in terms of the transistors. Okay, so for that, what we are going to do is we are going to divide the inner two layers. We are going to divide the inner two layers. Okay, that is N1 minus and P2. Okay, as a 50% here and 50% here. Okay, so if you check if we divide the inner two layers, then the structure will look like this. This is the structure we'll be getting. Okay. Okay. So it is like a P1, N1 by 2, P2 by 2. Okay. And here it is a N1 by 2, P2 by 2, and here it is a N2. You can check if we club these two structures. If we club these two structures, we'll be getting this full. Okay, PN device. Okay. Now you can check P1 is connected to the anode terminal. Next, N2 is connected to the cathode terminal, and the gate is connected to the P2, right? P2 layer. So here it is a gate, and these two are, yes, internally connected. These two are internally connected because we have divided this na N1 and P2 as 50% here and 50% here. So can we say that it is like this is a one transistor, that is a PNP transistor, and this is the second like a NPN transistor. Okay, so that's why it is a two transistor analogy. Okay, we have divided the four layers as a, yes, PNP and the NPN. Now from this, can we draw the equivalent circuit? We can draw the equivalent circuit like, yes, one is the PNP and second one is the NPN transistor. Right, this is a PNP. Yeah. Here it is an anode, here it is a gate, here it is a cathode. Okay, PNP. This is a PNP, and here it is a NP and N. So arrow should be here, and here it is a arrow. Okay, so you can check. Means whatever the structure we have drawn here, the same structure. Okay, in the equivalent circuit form, I have represented here. You can check. Here it is a N1 by 2, N1 by 2 are connected internally, right? So N-type layer of the first transistor is connected to the N-type layer of the second transistor. P-type layer of the first transistor is connected to the P-type layer of the second transistor. So here I have represented N of the first transistor is connected to the N-type of the second transistor. P type of the first transistor is connected to the P type of the second transistor, right? So it is an anode, gate, and cathode. Let us consider current here is a IG. Current flowing through the gate terminal is a IG. Consider current flowing through the anode terminal is a IA, and current flowing through the cathode terminal is a IK. Okay, is a IK. Now, if you check these two transistors, consider this as a Q1 transistor, this as a Q2 transistor, right? So can we say that for this PNP transistor, the anode terminal is nothing but the anode terminal. Yeah, anode terminal is nothing but the emitter terminal. Yes or no? Right? This terminal is like a base terminal, and this terminal is like a collector terminal. Okay, so emitter, base, and collector. Similarly, for this transistor, if we check, yes, the cathode terminal means this terminal is like a emitter for the second transistor. So it is like a emitter. The base for the second transistor is like this is the base terminal for the second transistor, and this terminal is like a collector terminal of the second transistor. Okay, so emitter, base, collector, collector, base, and emitter here. Let us consider the current flowing through the emitter terminal is IE1. Let us consider current here is IE1, because one subscript I am using because this is a transistor Q1. So IE1 is the current flowing through the emitter terminal of the first transistor. Consider current flowing through the base terminal of the first transistor is IB1, and consider the current flowing through the collector terminal of the first transistor is IC1. So IE1, IB1, IC1, these are the current flowing through emitter, base, and collector terminals of the transistor Q1, right? Similarly, let us consider the current flowing through the collector terminal of the second transistor is IC2. Okay, current flowing through the base terminal of the second transistor is IB2, and current flowing through the collector emitter terminal of the second transistor is IE2. So I'm considering this current is IE2, right? IE2. Is this clear? So we have indicated emitter, base, collector, right? Emitter, base, collector terminals for the both the transistors. We have considered the currents flowing through the emitter, base, and collector. So it is IE1, IB1, IC1, IC2, IB2, and IE2. Okay. Next. So here can we write IE1 is equal to IA and IE2 is equal to IK? Yes or no? Right. So IE1 is equal to IA. Okay. And IE2 is equal to IK. IE2 is equal to IK. Right. Because emitter for SCR we are having anode current IA. Okay. And the current flowing through the cathode we have considered it as a IK. Okay. So IE1 is equal to IA and IE2 is equal to IK. Right. Next. Now, in order to proceed further, we need to use the two basic equations, okay, from the transistor. These two equations are, first equation is emitter current is equal to base current plus collector current. Okay, so emitter current is equal to base current plus collector current. Yes, this equation is valid for transistor, any transistor. And second one is IC is equal to alpha into IE plus ICBO. Okay, where IC means collector current, okay, which is equal to alpha into IE, that is the emitter current. In the transistor wearing the alpha and beta terms, right? So that alpha here. And ICBO is nothing but collector to base leakage current, okay, when base terminal is open, right? So ICBO. Generally in the transistor operation we neglect this term, right? Because it is a leakage current only, okay, very small value. Now, so these two expressions we are going to use from the transistor, okay, basics of the transistor. Now here you can check if this is the expression for any transistor. So can we write for transistor Q1, instead of IC now we'll be having IC1, which is equal to alpha 1 into IE1 plus ICBO1. Similarly, we can write for transistor 2 also. Okay, so let me write for Q1. For transistor Q1. For transistor Q1, right? We can write for transistor Q1, we can write IC1 is equal to alpha 1 into IE1 plus ICBO1. Okay. And similarly for transistor Q2, we can write for transistor Q2, we can write IC2 is equal to alpha 2 into IE2 plus ICBO2. Okay, now consider as equation number 1, consider as equation number 2, right? IC1 IC2 expression means for transistor Q1 and Q2 we have written. Okay, now you can check here. We know IE1 is equal to IB1 plus IC1, and again IB1 is equal to what? IC2 na. Can we write IB1 is equal to IC2 because whatever the current here, the same current will be flowing here. So can we write IB1 is equal to IC2, and further we can write IE1 is equal to IC1 plus IC2 only, right? So let me write for Q1, for Q1 transistor Q1, we can write IE1 is equal to IC1 plus IB1. Collector current is equal to emitter current plus base current, right? So IC1 plus IB1. But IB1 means what? It is IC2 na. IB1 is equal to IC2 only. Okay, so we can write it is a IC2. So therefore IE1 is equal to IC1 plus IC2. Okay, now can we put this equation 1 and 2, that is IC1 IC2, in this expression? Yes, so put 1 and 2, put 1 and 2 in above expression, in above expression. So therefore we can write IE1. IE1 means what? It is again IA na. IE1 means IA na. We have written IE1 is equal to IA. Okay, so let me write it as IA is equal to IC1 is alpha 1 into IE1 plus ICBO1 plus IC2 means we have written IC2 is equal to alpha 2 IE2 plus ICBO2. Okay, alpha 2 into IE2 plus ICBO2. Okay, so further we can replace this IE1 with the IA, replace IE2 with IK na. You can check IE1 is IA, IE2 is IK. Okay, so we can replace IE1 with IA. So IA is equal to alpha 1 into IA plus ICBO1 plus alpha 2 into IK plus ICBO2. Okay, now here we're having a IK. You can check IK means this current. Okay, so if we consider this full as a single circuit, if we consider this full as a single circuit, for this circuit we are having two incoming currents. One is the IE1, that is the IA, and second one is the IG, and only one outgoing current we are having na. So can we write IK is equal to IA plus IG? Please listen it carefully. Okay, so if we consider this as a full as a single circuit, for this circuit we are having the two input currents. One is the IA, second one is the IG, and only one outgoing current we are having, that is the IK. So can we write IK is equal to IA plus IG? Yes, we can write. Okay, so IK is equal to IA plus IG. Replace this IK with the IA plus IG. So we can write it as alpha 1 into IA plus ICBO1 plus alpha 2 into IA plus IG plus ICBO2. Right? Now here it is the IA term, here it is the IA term, and at the left hand side also we're having the IA. Can we take all the IA terms to the one side? Yes, so it is like IA minus alpha 1 into IA minus alpha 2 into IA is equal to, we can write alpha 2 into IG. We have taken only alpha 2 IA to the left hand side. IG is as it is na, so alpha 2 into IG will remain here. Okay, alpha 2 into IG plus ICBO1 plus ICBO2 divided by, sorry, not divided by, yes, so this is the right hand side we will be having. Next, further we can write it as, from this we can take IA common, so therefore we can write IA into, it is like a 1 minus alpha 1 minus alpha 2, which is equal to alpha 2 into IG plus ICBO1 plus ICBO2. Okay, so further we can write it as, therefore IA is equal to alpha 2 into IG plus ICBO1 plus ICBO2 divided by this term. So this term we can write it as 1 minus in bracket alpha 1 plus alpha 2. Okay. This is the expression for the anode current. This is the expression for the anode current of the SCR. Expression for the anode current of the SCR in terms of gate current, leakage currents, okay, and alpha 1 and alpha 2. Now, yes, with the help of this expression and one curve, okay, one plot I am going to draw here. That plot will be between IE, that is the emitter current, versus alpha, okay, and that plot is valid for all the silicon transistors. Okay, so let me draw that plot. You can simply Google it. You will understand what is this plot is. Plot between alpha versus IE. Okay, alpha versus IE. IE means emitter current, and alpha is nothing but your what you can say, that is like your current gain, right? That okay, in a transistor. So for any transistor, silicon transistor, the plot between IE versus alpha, this is a standard plot, and this plot is valid. Okay, this relation is valid for all the silicon transistors. Okay, and the plot is like this. What is the maximum value of alpha? Maximum value of alpha is like a 1 only, right? That will be 1 only, right? Yes, this is a 1.0 and this is a alpha. So what this plot indicates, as value of IE increases, value of alpha increases, right? As value of IE increases, value of alpha also increases. Okay, this is the meaning of this plot. More the IE, more will the alpha, right? Now, with the help of this plot and whatever the expression we have derived, okay, that expression, we are going to discuss how the current flowing through the SCR increases from leakage current to the high value, okay, by a circulation of small gate current. Okay, circulation of small gate current. So now here, suppose initially the gate current will be 0. Suppose initially the gate current is 0 and our SCR is in a off state, right? Suppose initially gate current is 0 and SCR is in a off state. So let me write, initially suppose IG is equal to 0 ampere, SCR is in a off state. SCR is in a off state. So how much current that yes, we expect to flow? The when SCR is in a off state, only the leakage current will yes should flow. Yes or no? So now you can check here. If gate current is 0, if gate current is 0 means this alpha 2 into Ig term will become 0 only, right? If alpha to Ig term is 0, and if SCR is in a off state, if SCR is in a off state, what about the IE1 and IE2? If SCR is in a off state, then what about the IE1 and IE2? Definitely IE1, IE2 will be 0 only. Nearly IE1 and IE2 will be very small. Ideally speaking, 0, but practically that will be very small value because SCR is in a off state. So that's why these two transistors also will be in the off state. Gate current is 0, SCR is in a off state. So this transistor is in the off state. This transistor is also in the off state. So that's why current IE1 and IE2, okay, current IE1 and IE2 are nearly equal to 0, nearly equal to 0. So you can check if IE1 and IE2 are suppose nearly equal to 0. So what about the alpha 1, alpha 2? If IE1 and IE2 are nearly equal to 0, alpha 1 and alpha 2 are also very small, na? Alpha 1 and alpha 2 are very small. So if alpha 1 and alpha 2 are very small, what about this alpha 1 plus alpha 2 addition? That will be also very small. Alpha 1 plus alpha 2 addition is small. So that's why 1 minus this alpha 1 plus alpha 2, that will be nearly equal to 1 only. Yes or no? That will be nearly equal to 1 only. So now you can check here, if gate current is 0 and thyristor is in an off state, this denominator term will be nearly equal to 1. So IA is equal to only ICBO1 plus ICBO2. That is the leakage current, na? That is the leakage current. Yes or no? Let me indicate it. Yes, when gate current is 0, SCR is in an off state. What about the IA we have written? IA we are getting is equal to ICBO1 plus ICBO2. Means only leakage current is flowing through the SCR. Only leakage current is flowing through the SCR. Now, suppose in order to turn on the SCR, we have started circulating the gate current. Okay, so in order to yes, to initiate, let me write, to initiate turn on process, to initiate turn on process in SCR. In SCR, yes, we have started circulating the gate current, right? We have started circulating the gate current, right? Let me write it as a gate current circulated, gate current circulated in gate cathode circuit, right? In gate cathode circuit. Now let us understand how the circulation of small gate current, how the circulation of small gate current will help, okay, in building the current flowing through the SCR from leakage current to the high value. Because when your gate current is 0, we are getting this as a leakage current only, and IA is equal to leakage current, right? Now let us discuss. If IG is non-zero, suppose if IG is non-zero, IG non-zero means this alpha to IG term will be non-zero only. Yes or no, right? IG is non-zero, so alpha 2 into IG term will be non-zero. So let me write it as, first thing is alpha 2 into IG term will be non-zero, means it is increasing, it increases. Okay, so alpha 2 IG term increases. What about the IE2? What about the IE2? You can check. IE2 is nothing but addition of IA and IG, na? IE2 means what? Addition of IA and IG. That is nothing but your IE2. Okay, you can check here. IE2 we have written. Yes, IE2 means this current, which is equal to IE1 plus IG. But IE1 is nothing but IA, na? Okay, so IA plus IG. So if we increase the IG, whether the IE2 will increase, definitely the IE2 will increase. Okay, so let me write it as alpha to IG increases, means IG is non-zero, so therefore your IE2 will increase. If IE2 increase, what about the alpha 2? IE2 increases means alpha 2 also increase, na? Right? So therefore alpha 2 will increase. If alpha 2 increases, alpha 2 has increased, IG is now non-zero. Okay, so what about the IA? You can check here. IG is non-zero, alpha 2 has increased. So what about the IA now? IA is nothing but this term now. In this term, the numerator has increased. Alpha 2 also increased. So this difference 1 minus alpha 1 plus alpha 2, this difference will reduce, na? So that's why your IA will increase. IA is nothing but IE1. Okay, so IA in bracket, let me write it as IE1. This will increase. As IE1 increases, what about the alpha 1? Alpha 1 will further increase. Alpha 1 will further increase. Are you getting the point? Means IA increases, alpha 1 increases. So now again, IA increases. So what about the IE2? IE2 means what? IA plus IG, na? So if IA increases, what about the IE2? Further IE2 will increase. Means after this term, again IE2 will increase. IE2 increases, alpha 2 increase. Alpha 2 increases, again IA will increase. IA increases, alpha 1 will increase. So this term repeats, this term go on repeating. Are you getting the point? This loop go on repeating till anode current reaches the final value, that is the steady state value. Are you getting the point? Let me, yes, repeat this. This is very important. To initiate the turn on process in SCR, we have started circulating the non-zero gate current into the gate cathode circuit. So IG is non-zero. IG non-zero, so alpha 2 into IG term will become non-zero. That is that term will increase. As this term increases, your IE2 will increase. IE2 increases, alpha 2 increases. Alpha 2 increases, IA increases. IA increases, alpha 1 increases. Further, these two terms are increased, na? IA and alpha 1. These two terms are increased. So again IE2 will increase. IE2 increases, again alpha 2 increases. Alpha 2 increase means again IA will, or the IE1 increase. Alpha 1 increase, and this loop go on repeating, right? This loop, right, go on repeating, right? And at the end, we'll be getting the constant, that is the steady state anode current. Steady state anode current. Is this clear? Now in between, suppose if you remove this gate current, in between, if you suppose remove this gate signal, then also it will not affect on the conduction of the SCR, na? Because once this loop is repeating, in between, if you remove this term alpha to IG also, it doesn't affect on the operation of the SCR, on the conduction of the SCR. Is this clear? Right? So this is the two transistor analogy of the SCR, right? So next, now let us move towards the next point, that is a commutation. Commutation, SCR commutation, right? SCR commutation. Okay, so yes, all your doubts will be answered at the end of the session. Okay, next, so SCR commutation, already we have discussed about the turn on methods of the SCR. Now let us discuss about the commutation of the SCR. So first thing is commutation means turning off of a conducting SCR. That is nothing but the commutation. Okay, commutation means commutation. It is turn off of a conducting SCR. Conducting SCR, right? Turn off of a conducting SCR. That is nothing but the commutation. Now, in order to successfully turn off the SCR, we need to follow some certain steps. Okay, so we're having one procedure. So in that, let me write the procedure for commutation of SCR. Procedure for commutation of SCR. Commutation of SCR. Right. So first one. First of all, we need to reduce the anode current value of the SCR. Okay, that is the current flowing through the SCR. Okay, such that we need to reduce it such that that value becomes less than the holding current value. Okay, reduce anode current. Anode current. Anode current is nothing but SCR current. Okay, anode current of SCR such that IA becomes less than holding current value. Because from the holding current definition, if you recall, what is the definition of the holding current? It is the minimum anode current required to maintain the SCR into on state, otherwise it will turn off. So commutation means turning off of a SCR. Na? So if you want to turn off it, first of all, we need to reduce the anode current below to that of the holding current value. This is the first step. But from the dynamic characteristics of the SCR during turn off, we are having one point like, if we reduce the anode current value below to that of the holding current value, only doing this is sufficient to successfully turn off of the SCR? No. So for that, we need to maintain the reverse voltage now across the SCR, right? We need to maintain the reverse voltage across the SCR for the time TC, that is the circuit turn off time, which is greater than or equal to TQ, that is the device turn off time. Let me write it, then we will discuss. So second step is maintain reverse voltage. Maintain reverse voltage across SCR for time TC greater than or equal to TQ. We need to maintain the reverse voltage. Why the reverse voltage is required to be maintained across the SCR? Because for the removal of added charge carriers, na, right? So therefore TC and TQ. TQ means device turn off time. Let me write where TQ is a device turn off time. Device turn off time. And TC is a circuit turn off time. Circuit turn off time. Okay. So let us discuss how to find the TC. How to find the TC. So TC, that is the circuit turn off time. Circuit turn off time. Yes. It is the instant. Okay. It is the instant at which or it is the time interval. Let me write, it is the time interval measured from, it is the time interval measured from it is the time interval measured from, time interval measured from the instant, the instant at which current flowing through SCR, current through SCR, okay, becomes zero, becomes zero, becomes zero, okay, current flowing through SCR becomes zero. Let me write, or in practical case it is less than holding current, IA less than holding current. Theoretical case it becomes zero, okay, but practical case it is IA less than holding current, okay. It is the time interval measured from the instant at which current through the SCR becomes zero, and is from this instant, okay, and the time for which reverse voltage is maintained, reverse voltage is maintained across SCR, across SCR, okay. Means that circuit turn off time means it is the instant at which current flowing through the thyristor becomes zero. From that instant we need to measure, okay, the time during which or the for which the reverse voltage is maintained across the SCR, reverse voltage is maintained across the SCR. That is nothing but the TC. And for successful commutation of the SCR, for successful commutation of the SCR, TC should be always greater than or equal to TQ. If your TC is less than TQ, yes, SCR will not turn off successfully. Are you getting the point, right? For successful commutation of SCR, for successful commutation of SCR, for successful commutation of SCR, TC should be always greater than or equal to TQ. TC should be always greater than or equal to TQ. Okay. So how to turn off the SCR? We have discussed. First of all, we need to reduce the anode current value less than that of the holding current value. Second thing, we need to maintain the reverse voltage across the SCR for the time TC that should be greater than or equal to TQ. Right. Next, now we are having the two types of the commutation methods. First one is the natural commutation. Second one is the forced commutation. In the forced commutation, again we are having the three types. One is the load commutation. Second one is the voltage commutation. Third one is the current commutation. Okay. So one by one we are going to discuss. So let us first discuss the natural commutation. Natural commutation. Right. So let me write. Types of commutation. Types of commutation. First one is natural commutation. And second one is the forced commutation. Natural commutation means SCR turns off, okay, due to nature of the supply, due to the nature of the supply voltage. Okay, so that is the natural commutation. And the forced commutation means in order to turn off the SCR, right, we need to add the additional elements, we need to connect the additional elements into the circuit, okay, or we can say the those elements as the commutating circuits or the commutating elements. Okay, so important thing, natural commutation and forced commutation. Natural commutation is possible only when supply is AC, right? This is possible only when AC supply is there. AC supply means if for example consider we're having a rectifier circuitry. For the rectifier, input is a AC, output is a DC, na? Right? So for the rectifier circuitry, input is AC. So that's why the natural commutation of the SR is possible in rectifier circuitry. But whereas you can check the DC to DC converters, inverters, okay, in the inverter or the DC to DC converter, input is a DC. As the input is DC, right, means it is non-AC, it is non-AC, okay. So input is DC means in the DC to DC converter or second circuit or in the inverter, for those circuits we need to add the external elements into the circuit in order to turn off the SCR, okay. So for when the input is DC, when input is DC, then we need to go for forced commutation technique. So I'm repeating, natural commutation is due to nature of the AC supply, whereas the forced commutation is required in the circuit where the input is a DC, okay, input is a DC, right? So how to turn off the SCR if the input is a DC, then we will discuss after the natural commutation. So let us first discuss the natural commutation, right? Natural commutation. So yes, first natural commutation. So in order to understand the natural commutation, let us consider a simple circuit, okay? Suppose we are having a single phase AC supply, and here we are using a thyristor. This is a gate terminal, and here a resistive load. Consider a resistive load. This is a simple single phase half wave controlled rectifier. Yes or no? Right? So in this case, how the natural commutation is possible, we are going to discuss. So suppose load is purely resistive. Consider current here is a I0, voltage here is a V0, this voltage is a VT, this current is a IT, and supply current is considered as a IS. We are interested only in understanding the natural commutation. We are not interested in output voltage of the output voltage, that is the load voltage or the load current, right? We are going to focus only on natural commutation in this discussion, okay? So now here, as long as if I indicate in the circuit, if I indicate this type of symbol, so it is like an anode, cathode, and gate here, okay. So it looks like the gate circuit or the gate cathode circuit is open, but assume that the gate circuit cathode is connected there, okay. Some elements are connected there, okay. Means we need to assume that between gate and cathode we are having the circuit here. It is not shown here, but the circuit is present, okay. Now otherwise we cannot turn on the SR, na, right? So yes, let me draw the supply voltage. It is a Vm sin omega t. So it is a sinusoidal voltage, right? Vs, Vm into sin of omega t, 0 to pi and pi to 2 pi, right? Vs is equal to Vm into sin of omega t, okay. Let us consider at omega t is equal to 0, we have applied the gate signal to the SCR, okay. We are not interested in discussing how the SCR turns on by applying the gate signal, but we are interested in how the SCR turns off due to the nature of the supply, okay. So next, suppose the voltage across the thyristor waveform, we are going to draw this waveform and current flowing through the thyristor. Let us consider it as an IT. This is a pi, here it is a 2 pi, right? Here it is a pi, here it is a 2 pi, okay. Similarly, here it is a pi and here it is 2, right? Now, So we're having the supply voltage waveform. Vs is equal to Vm sin omega t. So you can check from omega t is equal to 0 to pi. Sin value will be positive na. Sin 0 is 0. Sin pi is 0. In between we're having yes sine of pi by 2, that is a peak value. After that sine of you can check 3 pi by 2. Okay. So we'll be getting this type of waveform for the supply voltage. That is the positive half cycle. Pi to 2 pi, supply voltage is negative. Okay, so we're having a positive voltage, we're having the negative voltage in the supply. Next, so this is the circuit we're having. Suppose during omega t is equal to 0 to pi, when supply voltage is positive, consider the polarity of the supply voltage is plus here and minus here. I'm saying that during 0 to pi, as Vs is positive, so we are considering the polarity of the supply voltage is plus here and minus here. Similarly, during pi to 2 pi, when Vs is negative, at that time we need to reverse these terminals, na? Yes or no? We need to reverse these terminals. Okay. So let us consider for 0 to pi, for omega t is equal to 0 to pi, for omega t is equal to 0 to pi. The supply voltage polarity is like a yes, upper terminal positive, lower terminal negative, and here we are having the thyristor. So this is a Vs, here it is a plus minus, this current is IT, this supply current is a Is, resistor V0 and I0, right? So Vs positive means we have considered plus here and minus here. Now you can check, it is like a highest potential point in the circuit, this is like a lowest potential point in the circuit. So you can check when Vs is positive, it is like highest potential is appearing at the anode of the thyristor. Lowest potential through the load is appearing at the cathode of the thyristor. So can we say that when Vs is positive, anode is more potential, more positive compared to that of the cathode? That is, the anode potential is higher than that of the cathode potential. So can we say that when Vs is positive, thyristor will be in the forward bias mode, right? So point to be noted, when Vs is positive, thyristor T will be in a forward bias mode. Forward bias. Okay. Now, as we know, in order to turn on the SCR by using the gate signal, what is the very first requirement? The first of all, we need to check whether SCR is in a forward bias mode or not. Yes or no, right? So when Vs is positive, thyristor is in a forward bias mode. So that's why we have applied the gate pulse to the thyristor at this omega t is equal to 0. Now this omega t is equal to 0 is nothing but your alpha equal to 0. What is this alpha and those things? We will discuss it while discussing your second chapter, that is the rectifier. Okay. For the time being, only consider at omega t is equal to 0, we have applied the gate signal. SCR is already in the forward bias mode and we have applied the gate signal. Now, if you check from pi to 2 pi, from pi to 2 pi, supply voltage is negative, na? So supply voltage is negative. Supply voltage negative means what will happen? It is like this will be minus and this will be plus. Upper terminal negative, lower terminal positive, na? Supply voltage negative means. So it is like a lowest potential here. Here it is a highest potential. Lowest potential will appear at the anode of thyristor. Highest potential through the load will appear at the cathode of thyristor. So anode is at a lesser potential than that of the cathode. So can we say that SCR will be in the reverse bias mode, right? So always keep it in mind here. When Vs is negative, thyristor is in a reverse bias mode. So suppose if thyristor is in a reverse bias mode, and if we apply the gate signal, whether our thyristor will turn on? No. So that's why here, when supply voltage is negative, we have not applied the gate signal to the thyristor. So we need to apply the gate pulse only when SCR is in a forward bias mode. That is when Vs is positive. I can apply the gate signal either here, at this instant, at any instant. Okay, at any omega t between 0 to pi, I can apply the gate signal. But here I have applied the gate signal at omega t is equal to 0. Okay. Now you can check at omega t is equal to 0. If we apply the gate signal, what will happen? Our SCR will turn on immediately, right? When SCR turns on, so when SCR turns on, this is the VT, voltage across thyristor. So it is like SCR is acting as a short circuit, na? SCR is in an on state means what? SCR is acting as a short circuit, right? So yes, for omega t is equal to 0 to pi, when gate pulse is applied here at 0, our SCR turns on. So SCR turns on means current will flow from supply voltage Vs, thyristor and the load. Current will flow in this loop, yes or no, right? So current is flowing here. So let me write first VT is equal to 0 volt because thyristor is acting as a short circuit. Okay, thyristor is acting as a short circuit. Here I am neglecting the on state voltage drop of the SCR. Okay, so Vt is equal to 0 volt, right? So now Vt 0 volt, and here the current is flowing from source towards the load. So can we apply KVL to this loop? You can check KVL to this loop is like plus Vs minus Vt minus V0 is equal to 0. KVL to the loop plus Vs minus Vt minus V0 is equal to 0. Okay, so KVL to loop. KVL to loop. So it is like a plus Vs minus Vt minus V0 is equal to 0. Out of that, Vt is 0. So what is the V0? So therefore, V0 is same as that of the supply voltage. V0 is same as that of the supply voltage. We have not drawn the waveform of V0. We can draw, but it is not required here. Okay. So V0 is Vs. Now you can check in this loop, I0, IT and IS, whether all these three currents will be same or different. All these three currents will be same only, na? Because we have only one loop we are having, and we have indicated three currents. So one loop we are having only, right? So can we say that I0 is equal to IT is equal to IS? All are same, right? So I0 is equal to IT is equal to IS. Let me write here. I0 is equal to IT is equal to IS is equal to what? I0 is the load current. According to the Ohm's law, load is a purely resistive, na? So according to the Ohm's law, what is V0? V0 is equal to I0 into R. So what is I0? I0 is equal to V0 by R. Yes or no? So let me write it as V0 by R, which is equal to, but V0 is equal to Vs, na? So can we write it as Vs by R? So therefore, point to be noted, IT is equal to Vs upon R. Thyristor current is equal to Vs upon R. Now during 0 to pi, how is the Vs? Vs is like this, na? This is the Vs we are having during 0 to pi. It increases, reaches the peak value and again decreases, right? So Vs is like this. V0 also will be like this only, na? Because V0 is equal to Vs. So how is the waveform of the IT now? IT will be Vs by R, na? So Vs by R means if Vs is 0, IT will be 0. As Vs increases, your IT also increases. As Vs reaches peak value, IT also will reach the peak value. And as Vs decreases, IT also decreases. At omega t is equal to pi, Vs is 0, IT also becomes equal to 0. Means very important, current flowing through the thyristor T, that is the IT, becomes 0 at omega t is equal to pi, right? And that is nothing but the first condition for the commutation has reached. What is the first condition for commutation? Current flowing through the thyristor should be less than the holding current value, na? So if at omega t is equal to pi, current flowing through thyristor is reaching the 0 value, means what? Definitely it will be less than the holding current value. So that's why we can say that the first condition for commutation has reached, right? Now let me write. So IT waveform, let us draw the IT waveform. The waveform of IT will be like this. The nature will be similar to that of the supply voltage, but the thing is magnitude will be different, right? Because this is like your Vs upon R. We have written IT is equal to Vs by R. So that's why here IT is equal to Vs by R. Vs peak value, definitely IT will be peak value. Okay. If R is greater than 1, then this value, okay, the this magnitude of the IT will be less than that of your Vs. If R is less than 1, IT will be greater than that of Vs. Okay. Now, so this is the IT. So now we can check at omega t is equal to pi, IT is 0. So it is like a first condition for commutation has reached. What about the Vt during 0 to pi? During 0 to pi, Vt is 0, na? We have written thyristor acting is a thyristor is in a on state, na? So Vt is equal to 0. Now you check after the pi, what will happen in the circuit? Because what is the second requirement? Second step we are having, we need to maintain the reverse voltage across the SCR, na? Why the reverse voltage is required to be maintained across SCR? In order to remove the added charge carriers, right? So now you can check after pi what is happening. After pi, supply voltage is negative, na? So if supply voltage is negative, we can draw for omega t is equal to pi to 2 pi. For omega t is equal to pi to 2 pi, supply voltage is negative. So polarity will be like this. Here it is minus, here it is plus. I have reversed the polarities. For 0 to pi, I consider upper terminal plus, lower terminal minus. Now I am considering lower plus, upper minus, means supply voltage is negative. Okay. So Thyristor current has already reached the zero value, so thyristor is in the off state only. Now what will happen to the thyristor? So this is the V0, this is the I0, this is the IT, this one is the IS, and this is the VT. This is the VT wiring, right? Now you can check here, this is supply voltage VS. As thyristor is in an off state, why the thyristor has turned off? Because its current becomes less than that of the holding current value at omega t is equal to pi, right? So that's why thyristor has turned off. Now we need to check for successful turn off of a thyristor. Definitely we need to maintain the reverse voltage for a time tc greater than or equal to tq na, right? So now thyristor has turned off here, no problem. But let us check for how much time interval, the reverse voltage will appear across the thyristor. Okay, reverse voltage will appear across the thyristor. So you can check minus here plus here. Okay, so it is like lowest potential will appear at the anode of thyristor, highest potential will appear at the cathode of thyristor, right? So now in this circuit, what is the current? Thyristor is acting as an open circuit, so that's why IT is equal to IS is equal to I0 is equal to 0 ampere only. Next, can we apply KVL to this loop? KVL to this loop. So it is like a minus VS minus VT minus V0 is equal to 0. KVL to loop. Okay. KVL to loop. Now you can check here. If I0 is 0, what about the V0? According to Ohm's law, V0 is equal to I0 into R. So if I0 is 0, so V0 will be equal to 0. So this V0 will be 0 only. So therefore, can we write VT is equal to minus VS. So voltage across thyristor will be negative. Voltage across thyristor will be negative, right? Please be careful. Don't get confused. VT is minus VS. The meaning is not like this is a minus of. You can check here if VS is negative here, na. So it is not like minus of this minus. So that will be plus. It is not like that, because this thinking or in this way, if you think, then it will be your mistake. Why I am saying? Why? Because for pi to 2 pi, we considered we reverse the supply voltage polarity na, it is like a minus here plus here. So if from pi to 2 pi, suppose from pi to 2 pi, if we don't reverse the polarity of the supply voltage, then we can say here VT, then here you will be getting it as a VT is equal to VS. And in that case, you can say if the supply voltage polarity is not reversed, then whatever here negative, then definitely that negative will appear here. But now in this case, this supply voltage was reversed. The meaning is this plus this minus, and we're considering this value as a plus only. This value as a plus only. So here VT is minus VS. The waveform for the VT will be like this only. Waveform for VT, that will be negative only. This will be your minus VS. Minus VS. Right? Don't get confused. Here minus VS is not the doesn't mean that minus of that VS value during pi to 2 pi. You can check VS during pi to 2 pi, it is negative. So minus of that negative value will be positive now, right? So it is not like that, because here we have reversed the polarity of the supply voltage during the minus value, negative values of the VS. So that's why if this minus here minus VS, then definitely that VT will be your negative only. VT will be negative. Now you can check here. Yes. After once the current becomes to the thyristor reaches zero value at omega t is equal to pi. After that, what is the second requirement? We need to maintain the reverse voltage. Na? So you can check whether the reverse voltage is maintained here or not. Yes, reverse voltage is maintained. And how the reverse voltage is maintained? Due to the nature of the supply. Na? Are you getting the point? Right? So that's why it is a natural commutation. You can check in the circuit. In the circuit, we are having only source, load, and the switch. Na? We are having source, load, and a switch. Apart from the source, load, and the switch, any other element is present in the circuit? No. So for the natural commutation, external elements for the commutation of the SCR are not required. Okay, right? So natural commutation is due to the nature of the source, nature of the supply. Is this clear? Right? Next. So let me write here. Just a minute. Okay, so here let me write two statements. at omega t is equal to pi, at omega t is equal to pi, yes, current flowing through SCR, current through SCR becomes 0 or reaches 0 value, becomes 0. So it is like a first condition for commutation, for commutation of SCR. First condition for commutation of SCR has reached, right? Okay. First current becomes 0. The first condition for the commutation of SCR has reached, right? So, next, second, from omega t is equal to pi to 2 pi. From omega t is equal to pi to 2 pi. Yes, during pi to 2 pi, what is happening? The reverse voltage is maintained, right? During pi to 2 pi, reverse voltage is maintained across SCR, across SCR. So that is nothing but what? Second condition for commutation has reached. Okay, so it is like a second condition for commutation of SCR has reached. Now, can we find the circuit turn off time in this case? Circuit turn off time, TC, circuit turn off time, that is a TC. So, how to find the circuit turn off time? Yes, just now we discussed the. First of all, we need to check the instant at which current flowing through thyristor becomes 0. So current flowing through thyristor is becoming 0 at omega t is equal to pi. After this instant, check till which instant the reverse voltage is maintained across SCR. So from pi till which instant the reverse voltage is maintained? Till 2 pi. Na? So from pi till 2 pi, the reverse voltage is maintained across the SCR. So this indicates from here to here, this indicates the TC, that is a circuit turn off time for thyristor. Okay. If you check from pi to 2 pi, now we are having the angle. We need to find the time now, because it is a circuit turn off time. Okay. So angle is like a 2 pi minus pi. So corresponding this angle is pi. So what is the time? Angle means omega t, right? So therefore, what is the time? Time is equal to angle divided by omega. Na? So therefore, TC is equal to, we can write it as 2 pi minus pi. That is a pi divided by omega. Let me write TC is equal to 2 pi minus pi divided by omega, right? Angle divided by omega is nothing but your time. So it is equal to pi by omega. Pi by omega. This is the circuit turn off time. Okay, circuit turn off time for the thyristor. And this is valid only for this circuit, right? This is valid only for this circuit, whatever we discussed. It is not like that for a natural commutation. Blindly, if you write the circuit turn off time is pi by omega, no. Circuit to circuit, it will change. Okay, circuit to circuit, it will change. Is this clear? So how to find the circuit turn off time? First of all, we need to check the instant at which current flowing through thyristor becomes 0. And after that, till which instant the reverse voltage is maintained. So from this instant, if you check, after from pi, yes, we are having the reverse voltage across the thyristor and it is maintained till 2 pi. Na? So thyristor is in a reverse bias mode from pi to 2 pi actually. So reverse voltage is maintained from pi to 2 pi. So that's why the circuit turn off time means what? Yes, it is a 2 pi minus pi, means this angle divided by omega. So 2 pi minus pi by omega means it is a pi by omega only, right? So that's why it is a pi by omega, right? So in the rectifier circuit, for all the circuits, okay, we are going to discuss for all the circuits, we need to find the circuit turn off time, okay? So at that time, we will understand better, okay? So next, let us discuss the forced commutation technique. So as I said, the forced commutation technique is required in Yes, when the input is DC. If the input is DC, then the force of commutation technique is required. Yes or no, right? So let us first discuss the load commutation or self commutation. Okay, load commutation or self commutation. So input is a DC. Suppose here we are having a thyristor. And additional elements we have connected here L and C. And suppose the load is a resistive. We are having the two circuits actually here. This is a load resistor. Let me write it as a load resistor. And here L and C. This is a thyristor T. This is a VDC. Okay, let me write it as a VS. Current flowing through thyristor is a IT. And voltage across thyristor is a VT. Okay, so let me show here. These are L and C. These are the commutating elements. These are the commutating elements. Okay, and load resistor. This circuit is for low value of RL. For high value of RL, the circuit will be different. Okay, that we'll discuss after this. Okay, so this is for low value of RL. Low value of RL. That is a load resistor. So now, yes. So let us discuss here the force commutation technique, in that the load commutation or the self commutation. Input is a DC voltage Vs, thyristor T. Okay, so here it is a supply, here it is a main switch, that is a thyristor, and here we are having a load. Apart from source, thyristor, that is a main switch, and a load, whatever the elements we are having, that is the inductor and capacitor. These are the additional elements we have connected in order to turn off the thyristor, right? Whereas if you check in the natural commutation, additional elements were not connected, right? Only we had three elements, na? Source, thyristor, and the load. But here the two additional elements were connected. Okay, so commutating elements. Now let us discuss the circuit operation. Suppose for t less than 0, thyristor will be in the off state. Okay, and circuit will be at the rest position. Let me write for t less than 0. For t less than 0, yes, thyristor or SCR is in a off state. SCR is in a off state, right? Next, circuit will be at the rest position. Circuit at rest position. Okay, so for t less than 0, it is like a current was not flowing from source towards the load. So inductor has not stored any energy, capacitor has not stored any charge. Okay, so that's why circuit was like a rest position. Okay, now at t is equal to 0, we are going to apply the gate pulse to the SCR, right? At t is equal to 0, we are going to apply the gate pulse to the SCR. Now check, when we apply the gate pulse to the SCR at t is equal to 0, whether at t is equal to 0 our SCR will turn on immediately or not. If we apply the gate pulse and if SCR is in a forward bias mode, then and only then our SCR will turn on. Na? So you can check here, when thyristor, before t is equal to 0, if you check, this is a plus, this is a minus. So it is like a higher potential, here it is a lower potential. Higher potential is appearing at the anode of thyristor, lower potential through the load will appear at the cathode of thyristor. So can we say that for t less than 0 also, even our thyristor was in a forward bias mode only. So therefore at t is equal to 0, if we apply the gate pulse, our thyristor will turn on immediately. Okay, so let me write, at t is equal to 0, the gate pulse is applied to thyristor. At t is equal to 0, yes, gate pulse applied to thyristor and thyristor turns on. Thyristor will turn on, okay, by applying the gate signal, right? So for at t is equal to 0, what will happen? It is like a thyristor will turn on. So thyristor will act as a short circuit. What about the status of inductor and capacitor at t is equal to 0? At t is equal to 0, what is the behavior of inductor and capacitor? Before t is equal to 0, it was like a current flowing through the inductor was 0. Voltage across the capacitor was 0. Na? So at t is equal to 0, even though the switch is closed, this inductor will behave as open circuit or short circuit. Come on. Yes, capacitor will act as an short circuit, inductor open circuit, yes or no, right? So same from transient analysis where, because capacitor opposes the sudden change in the voltage, inductor opposes the sudden change in the current. Okay, so at t is equal to 0, this will act as an open circuit, this will act as a short circuit. Okay, so let me draw the circuit, equivalent circuit at t is equal to 0 also. So at t is equal to 0, if you check the circuit will be like this. This is an open circuit, this is like a short circuit, and here we are having RL. RL value is less, right? Low RL we are having. So this is a VS, this is a thyristor, this current is IT. Okay, this is an inductor, and here it is a capacitor. Inductor is acting as an open circuit, capacitor acts as a short circuit. Okay, now for t greater than 0, what will happen? T greater than 0, it is like this will act as an inductor, this will act as a capacitor, na? Because inductor go on storing the energy, capacitor go on charging, na? Right? So for t greater than 0, we can draw the circuit. It will be like SCR is in a on state, here it is inductor, here it is a capacitor, and here it is a load resistor RL. Supply voltage is DC, right? This is a VS. Here we are having the supply voltage. Okay, this is a VS. Here it is a thyristor T. This current is IT, inductor L, capacitor C, and a low value of resistor RL. Low value of resistor RL. Now consider current in the circuit is I. Current in the circuit is I, right? So it is like for t greater than 0, what is happening? Inductor go on storing the energy, capacitor go on charging. Okay, so now can we apply KVL to this loop? Yes, KVL to loop. Let me write here. KVL to loop. It is like a plus VS minus thyristor is in a on state, na, so voltage will be 0. So minus L into di by dt minus 1 by C integration of I into dt minus RL into I is equal to 0, right? RL into I is equal to 0. But if you check in this circuit, as RL is low, so therefore voltage across RL will be very less compared to that of your voltage across inductor and voltage across capacitor. Okay, so we are going to neglect it. So let me write as RL is low, so therefore voltage across RL, so I into RL, that is nothing but voltage across load. Voltage across load is very, very less than compared to that of your VL and VC. Okay, compared to that of your VL and VC. Now, so if we neglect this term, therefore I into RL is neglected. So if we neglect this term, so can we write therefore VS minus L into di by dt minus 1 by C integration of I into dt is equal to 0. Okay, so further we can write it as taking Laplace transform. Okay, we need to simplify it now for current. Okay, and next we are going to derive the expression of the VC also, voltage across capacitor. Okay, so taking Laplace transform on both sides. Right hand side we are having only 0 na, so that's why the Laplace will be 0. So here it is a VS by S minus L into S into I of S minus 1 by CS into I of S is equal to 0, right? So now we can write it as therefore VS by S is equal to LS plus 1 by CS into I of S, correct? Can we take the cross multiplication? Yes, so therefore VS by S is equal to like LCS square plus 1 upon CS, okay, into I of S, right? So therefore we can write yes will get cancel out. Okay, so therefore VS is equal to, now can we make the coefficient of S square is equal to 1? Yes, so for that we need to take this LC common. So if we take LC common, so it will be like S square plus 1 by LC. Are you getting the point? I have taken this LC common. Okay, so that's why it is LC into this term divided by C into I of S. So this C and this C also will be getting cancelled out. So therefore Vs is equal to L into S square plus 1 by LC into I of S. So therefore I of S is equal to Vs upon L into, we can write it as 1 upon S square plus 1 by LC. Yes or no? Now, can we adjust this term? Can we adjust this term so that this term will become, or the Laplace inverse of this term will become some function in the time domain? Right? Currently, if you check for this term, if we take the Laplace inverse, we will not get anything. Okay, so we need to do some adjustment here. So what the adjustment? You can check what is the Laplace of sin 80. Laplace of sin 80 is, yes, it is a upon s square plus a square. Na? So in this case, instead of a, yes, we are having it is like 1 by LC. We are having a 1 by LC. So for that, what we are going to do? So therefore, I of s is equal to Vs upon L into, I am going to multiply numerator and denominator, okay, with the 1 by root LC. So it will be like 1 by root LC here divided by s square plus 1 by LC, okay, and again we need to divide it with 1 by root LC. So it is like 1 upon root LC. So you can check, if we cancel out this 1 by root LC, we'll be getting again this term, na? Right? So now we can write this term as, therefore we can write, therefore I of s is equal to, it is a Vs upon L into 1 by root LC means it is a into root LC. Yes or no? That will be into root LC into, we can write it as a omega 0 upon s square plus omega 0 square, where omega 0 is equal to 1 by root LC. Omega 0 is 1 by root LC. Okay, means I have replaced this 1 by root LC with omega 0. Okay, next. So now you can check Vs by L here, and here it is root LC. So one root L will get cancelled out now from here. L is nothing but root L into root L. So one root L will get cancelled out. So therefore I of s is equal to Vs into under root C by L. This is a C divided by L into, we can write omega 0 upon s square plus omega 0 square. Okay, so omega 0 upon s square plus omega 0 square. Right? So now can we take the Laplace inverse? What is the Laplace inverse of this term? It is a sine of omega 0 t. Yes or no? Right? So taking inverse Laplace transform, taking ILT means inverse Laplace transform on both these sides. Okay, so it is a I. Inverse Laplace of I of s is I is equal to Vs into under root C by L into sine of omega 0 t. This is your current in the circuit. You can check in the circuit we are having the DC supply, but the current we are getting is a sinusoidal. Current we are getting is a sinusoidal. Why it is sinusoidal? It is due to the your inductor and capacitor, whatever the elements we have connected, na, due to that, right? So it is like your circuit will behave as an underdamped type of circuit. Okay, we will discuss this, what is underdamped and those things in the inverter chapter actually. Okay, so it is a Vs under root C by L into sine of omega 0 t. Now you can check this current I. Current I is nothing but, this is a loop current. This is a loop current. Can we say that this I is nothing but IT only? Can we say that this I is equal to IT? Right? So therefore IT is equal to I is equal to Vs into under root C by L into sine of omega 0 into t. Sine of omega 0 into t. This is a current through the thyristor. Current through thyristor. Or SCR you can say. Current through SCR. Yes. Now current through the SCR is a sinusoidal. No? Current through SCR is sinusoidal. So at omega 0 t is equal to 0. At omega 0 t is equal to 0. Sine of 0 will be 0. Current will be 0. After that, current go on increasing slowly. at omega 0 t is equal to pi by 2, right? That is t is equal to your pi by 2 omega 0. Okay, so at that instant current will reach the peak value, and after that current will decrease. So having the nature for current, you can check here. Current it nature will be like this. This is a time. Let me write it as a time. Okay, you can write in the form of time or in the form of omega 0 t, doesn't matter. Okay, so right, so here you can check. This instant is nothing but your pi by omega 0. This instant is like your pi by 2 omega 0. Means at t is equal to pi by omega 0. You can check here, put t is equal to pi by omega 0. You will get sine of omega 0 into pi by omega 0. It is like sine of pi. Sine pi is 0. So that's why it is a 0. At t is equal to pi by 2 omega 0. It is like sine of omega 0 into pi by 2 omega 0. Sine of pi by 2. So that is the peak value. No? What is peak value here? Peak value is equal to Vs under root C by L. Na? This is a peak value. Yes or no? So it is a Vs into under root C by L. C by L. Right? So this is the current in the circuit. Now you can check at t is equal to pi by omega 0. At t is equal to pi by omega 0. Current flowing through thyristor becomes 0. The meaning is first condition for commutation has reached. Yes or no? Right? So this is like a first condition for commutation has reached. Okay. Next. Now can we say that from here to here it is like our thyristor is in a on state. Thyristor is in a on state. Now again next what will happen to the after pi by omega 0 to the thyristor we will discuss. Okay. Because second requirement is we need to maintain the reverse voltage now. Right? So let us check whether the reverse voltage will be maintained across the thyristor or not after this instant. Okay. So now you can check during this interval, that is from t, for t greater than 0, current was flowing like this. The capacitor was like charging. Na? Capacitor was like charging. So consider the voltage across capacitors plus here minus here. This is the VC. Can we write the capacitor? Can we derive the expression for the VC now? VC is equal to 1 by C integration of IC into dt. Yes or no? VC means voltage across capacitor. It is equal to 1 by C integration of IC into dt. Right? So let me write it as VC, voltage across capacitor. Voltage across capacitor. Yes, VC is equal to 1 by C integration of IC dt. Now after t is equal to 0, capacitor is charging. Na? So put the limit 0 to t. Put the limit 0 to t. So 1 by C integration over 0 to t IC into dt. What is IC? IC is nothing but in our case it is a I na, because which current is flowing through the capacitor? It is a I. So that's why we need to write here instead of IC, we need to write the I only. Next, now we can replace this I with whatever the expression we have derived. So therefore VC is equal to 1 by C integration over 0 to t. What is IC? Vs under root C by L into sine of omega 0 t into dt, right? Into dt. We can take this outside because this is a constant, Vs under root C by L. So you can take it outside. So it is equal to VC is equal to Vs under root C by L and divided by C. Na? So it is 1 by C into Vs into under root C by L. Integration of sine of omega 0 t minus cos of omega 0 t. Right? So it is a minus cos of omega 0 t divided by omega 0 na, because the integration is with respect to time. And here we are having the omega 0 t. So that's why we need to divide with omega 0. Limit 0 to t. So therefore we can write VC. Now here it is divided by C. Here it is a under root C. Right? So root C will get cancelled out. So that will be like Vs into, it is like 1 by root LC. Root LC. Right? Into, this is the omega 0 we are having. Omega 0 means again it is a 1 by root LC. Na? So we can write it as 1 upon 1 by root LC. This term is there. Into, put the limit. It is like a minus cos of omega 0 t and minus of that term. Okay, so it is like 1 minus cos of omega 0 t. You can check. So this 1 by root LC, this 1 by root LC will get cancelled out. So therefore VC is equal to Vs into 1 minus cos of omega 0 t. This is your VC, voltage across capacitor. We have derived the expression for current flowing through the thyristor. Here it is a voltage across capacitor. Now you can check. First thing is current flowing through thyristor becomes 0 at t is equal to pi by omega 0. So you can check here at t is equal to pi by omega 0. What is the voltage across capacitor? At t is equal to pi by omega 0, what is the voltage across capacitor? At t is equal to pi by omega 0, Vc is equal to, yes, we can write Vs into 1 minus cos of, yes, it is like omega 0 into pi by omega 0, na? So it is like cos of pi. What is cos pi? Cos pi is -1, na? So 1 minus of -1, that is a 2. So therefore Vc is equal to 2 Vs. Vc is equal to 2 Vs. So point to be noted. Capacitor will be charged to the voltage of 2 times the supply voltage. Capacitor will be charged to the voltage of 2 times the supply voltage. Okay. Current flowing through thyristor becomes 0 at t is equal to pi by omega 0. Okay. So at t is equal to pi by omega 0, can we draw the circuit? You can check. Here at t is equal to pi by omega 0, what is happening into this circuit? First of all, current flowing through thyristor becomes 0. And at the same instant, to what voltage the capacitor is charged? Capacitor is charged to the voltage of 2 Vs now, with polarity plus here minus here. Now you can check here the current flowing through thyristor becomes 0, means thyristor will act as an open circuit now. So what is the voltage across thyristor now? Voltage across thyristor is Vt. Voltage across thyristor is a Vt. So plus minus here it is a Vt. So this voltage is 2 Vs. This voltage is Vs. So what is the Vt now? Vt will be equal to Vs minus 2 Vs. That is equal to your minus Vs. Vt is equal to minus Vs. Let me draw the circuit. At t is equal to pi by omega 0. At t is equal to pi by omega 0. Right? At t is equal to pi by omega 0. Yes, we can draw the circuit as supply voltage is DC, right? It is not AC. First of all, current is 0, so thyristor will act as an open circuit. Inductor, capacitor, and here it is a load. This voltage is Vs. Here it is current IT. This is a Vt, inductor L, capacitor C. Capacitor has charged to the voltage of 2 Vs. So this is a 2 Vs and this is a RL. Now you can check. Once current flowing through thyristor becomes 0, right? After that, what is the Vt here? Vt, you can apply KVL to this loop. KVL to this loop. Current in the circuit is 0 now. So IT is equal to 0 ampere. We have derived the expression for the IT, right? Okay, so at t is equal to pi by omega 0, IT is 0. Thyristor will act as an open circuit, right? Apply KVL to the loop. KVL to loop. We'll be getting it as plus Vs minus Vt minus 2 Vs is equal to 0. As current flowing through the circuit is 0, whatever the inductor current, inductor voltage, L di by dt. Because what is happening here in this circuit, current has reached the 0 value. And after that, this capacitor will try to discharge, but discharging path is not available. Because this, for this thyristor, it is like a cathode will be at more positive than that of the anode. So thyristor will not allow the reverse current now. So that's why capacitor will not discharge. So as the capacitor is not discharging, thyristor is in an off state. So whatever the current in the circuit, it will be 0. So that's why voltage across inductor will remain 0, right? Whatever the voltage across load, according to Ohm's law, current is 0. So that's why voltage across load will be 0, right? So only thing is we need to consider supply voltage, thyristor voltage, and capacitor voltage. So if you check from this, therefore Vt is equal to how much? Vs minus 2 Vs. It is equal to minus Vs. So Vt is minus Vs, whether it is a positive voltage or negative voltage. It is a negative voltage now. So can we say that, yes, the second condition, second requirement for the commutation has reached, that is the negative voltage is appearing across the thyristor. Is this clear? Now in this case, yes, in this case, as the discharging path is not available now, discharging path is not available for the capacitor. So that's why capacitor will hold that same voltage, that is a 2 Vs. Capacitor will not discharge at all because the discharging path is not available. So in this circuit, can we say that the circuit turn off time? Because after t is equal to pi by omega 0, across the thyristor, the reverse voltage will be maintained for remaining all time. So that's why your circuit turn off time will be like your infinite, right? Unless and until we connect the another circuit here for the discharging of the capacitor. Okay, till that instant our capacitor will hold the same voltage, that is a 2 Vs, because discharging path is not available, right? So this is the, yes, class, you can say the load commutation, okay, or the self commutation for low value of RL, for low value of RL. Is this clear? Always keep it in mind. Even though the supply voltage is DC, but we are getting the current is a sinusoidal. Current in the circuit is sinusoidal. And similarly, at t is equal to pi by omega 0, what is happening? This capacitor has charged to the voltage of 2 times the supply voltage. Supply voltage is Vs, but at what voltage the capacitor is charged? Capacitor has charged to the voltage of 2 times Vs. Is this clear? Right? Next. Now, at t is equal to pi by omega 0, how SCR is open circuit? SCR is open circuited because its current becomes 0 na? You can check latching current definition, sorry, holding current definition. If the current flowing through the SCR becomes less than the holding current value, so it is like your SCR will turn off. SCR turns off means what? It open circuits na? SCR has turned off, SCR has open circuited, but now the second requirement is we need to check whether it has successfully turned off or not. And for that, we need to check whether the reverse voltage will be maintained for sufficient time or not. Right? As soon as current flowing through SCR becomes 0, your SCR will act as an open circuit only. Here, what is happening actually? You can check. Yes, once SCR open circuit, once SCR open circuited, whether this capacitor after charging here, plus here, minus here, this capacitor will try to discharge. Yes, this capacitor will try to discharge in this loop, na? Because how the capacitor charges and how it discharges, you can check. Suppose for the capacitor, if I apply the voltage like this is a battery voltage. Suppose this is a 5 volt, and here we are having a capacitor. While charging, how the capacitor charges, it will be like this, na? So it is a plus here, minus here. Capacitor will be charged to like this, plus here, minus here. And how the capacitor discharges? Suppose if I reduce this voltage from 5 volt, right, to the, let us consider 2 volt. If I reduce this voltage from 5 volt to the 2 volt, then what will happen? Again, our capacitor will discharge, na? But how the capacitor discharges? Capacitor will discharge in this loop, na? For the capacitor, always keep it in mind. For the charging of the capacitor, we are having the current in one direction. For the discharging of the capacitor, the current will be in the opposite direction. Whereas in the inductor, when inductor stores the energy, when inductor stores the energy and when inductor releases the energy, in both the cases, the direction of current flowing through the inductor is the same only, because inductor is the element which opposes the change in the current. Yes or no? So that's why inductor will try to maintain the direction of the current in the same direction of the current. Yes, unchanged. That is the same direction. But whereas capacitor is the element which opposes the change in the voltage. So in the case of capacitor, what happens? Yes, it is like when capacitor charges, the current will be like in the anti-clockwise direction. And for the discharging of the capacitor, suppose if I reduce this voltage to the 2 volt, then definitely initially this capacitor will be charged to the voltage of 5 volt now. When this is a 5 volt, our capacitor in steady state will be getting charged to the voltage of 5 volt. In order to provide the discharging path for the capacitor, then what will, suppose I am reducing this voltage from 5 volt to the 2 volt. Then it is like this is a 5 volt, this is a 2 volt now. So that's why current will flow from high voltage to the low voltage, means capacitor will discharge like this. Okay. So for charging, current was anti-clockwise. For discharging, current is, it is a clockwise. So opposite current. So same thing here. When capacitor charges, means when thyristor was in an on state, it was like capacitor was charging here. Current was in a downward, current was in a clockwise direction. But when capacitor charges to the 2 Vs and when this thyristor will be in the off state, that is the open circuit, this capacitor will try to discharge in this loop in anti-clockwise direction. But whether this thyristor will allow the reverse current through it, because for thyristor here it is anode, here it is a cathode, na? So whether our thyristor will allow the current from cathode to anode? No. So that's why, yes, current will not flow here. So that's why our capacitor will hold the same voltage, that is a 2 Vs. Now, as the capacitor is not discharging, thyristor is in an off state. What about the current flowing through the inductor? That will be zero only now for all time. After t is equal to pi by omega 0, what is the voltage across thyristor? What is the current flowing through the inductor? Current flowing through the circuit, which is equal to current flowing through the inductor, which is equal to current flowing through the capacitor. That will be zero only after t is equal to pi by omega 0. If the current flowing through the inductor is zero for after t is equal to pi by omega 0, then what about the change in the current? Change in the current is zero only, na? Because current is zero for all the time, remaining time. So that's what about the di? Di will be zero, 0 minus 0, that is the zero only. So that's why your L di by dt, that is the voltage across inductor, will be zero only. Is this clear? Right? So okay, right? So remaining questions will discuss after the session. Okay, is this clear? The important thing is supply voltage is DC, but the current we are getting in the circuit is a sinusoidal. Current in the circuit we are getting is a sinusoidal, right? So that's why here capacitor will not discharging path is not available. So that's why your TC, if you check, TC will be your infinite in this case, right? Next, let us discuss what will happen if the load is if the REL is high. If the REL is high, right? We'll take a break after some time. Okay. Circuit turn off time. I have just now I told. Okay. Satish, circuit turn off time is infinite in this case. Why? Because if you check here, if I want to draw the VT waveform, how it will be? VT waveform T 0, 0 to it is like a pi by omega 0, and after that till infinity. Okay. So during 0 to pi by omega 0, your VT is 0, na? Thyristor is in on state, so VT is 0. After that, you can check VT is negative, na? This voltage is minus Vs. And as capacitor is not discharging, so that's why capacitive voltage will remain 2 Vs only. This voltage will be Vs only. So what about the VT? VT is Vs minus 2 Vs. So it is a minus Vs only, right? VT is equal to minus Vs, whatever we discussed. This voltage will remain as it is, okay, till infinite time. Okay, so that's why here TC will be infinite. TC will be infinite in this case. Okay, next. But suppose if we do some arrangement and if we provide the discharging path for the capacitor, then your TC will be different. But in this case, whatever the circuit we considered, for this circuit, definitely it will be infinite. Right? Next, let us discuss when load resistor is high, then what will happen? Okay, load resistor is high, then what will happen? So for high RL, for high value of RL, the circuit is like this. Thyristor, same inductor is here. Here it is a load resistor RL, and here we have connected a capacitor. This is a Vs. This is a thyristor T. Voltage across thyristor is Vt. Current from thyristor is It. This is a L. This is a C. Consider this current is IC. REL. This is a high load resistor, high RL. And this is a Let us consider the load current is I0. Okay, consider this current is IL. Okay, now for t less than 0, again the circuit, yes, it is like a circuit will be at the rest position. Okay, so for t less than 0, for t less than 0, circuit will be at rest position, will be at rest position. Rest position means your thyristor will be in the off state. Thyristor will be in the off state. Inductor has not stored any energy. Capacitor has not charged at all. Okay. Next, for t greater than, for at t is equal to 0, thyristor is turned on. At t is equal to 0, thyristor is turned on. So as soon as thyristor turns on, yes, what will happen? Current will flow from source, thyristor, inductor, capacitor, and yes, some part of the inductor current will be flowing through the load. Okay, right? In this loop, the current will be flowing. So for t greater than 0, if you draw the circuit, for t greater than 0, if we draw the circuit, it will be like this. This is Vs. Here it is a SCR, inductor, capacitor, and here it is a RL. RL is high, we have considered here. So this is a Vs, this is a thyristor, inductor, IL, IT, capacitor, and here it is a IC. This is a RL, and this is your I0. Now you can check, as RL is high, definitely your I0 will be less. As RL is high, definitely I0 will be very less. Okay, if I0 is less, can we say that most of the current, most of the inductor current will be flowing through the capacitor only, right? So let me write here or apply KCL first here. So IL is equal to IC plus I0, right? But this, as RL is high, therefore I0 will be very, very less than that of the IC. Okay, so now we are going to neglect the I0. So therefore I0 neglected. In the previous case, we neglected V0. Now we are going to neglect the I0. So if I0 is neglected, can we say that IL is nearly equal to IC only? IL is nearly equal to IC. Okay, so you can check, if we apply KVL to this loop, KVL to the loop 1, okay, then what is the equation? KVL to loop 1. KVL to loop 1. So we'll be getting it as plus Vs minus L into DIL by dt. Okay, minus L into DIL by dt minus 1 by C integration of IC into dt is equal to 0. Okay, but this IC is nearly equal to IL, na? So therefore we can write Vs is equal to L into DIL by dt plus 1 by C integration of IL into dt only. You can check this expression, and whatever the expression we wrote in the single, in that case, that is the for low value of RL, after neglecting the voltage across load, the same expression we are getting. Instead of IL there, yes, we have written I. Instead of IL, we have written I. You can check here. Yes, you can check this expression. Whatever this expression we are having, and the expression which we wrote just now. Okay, so Vs is equal to L into di by dt. If I shift these two terms, okay, to the right hand side, so it will be like Vs is equal to L di by dt plus 1 by C integration of I dt. Na? Now instead of I, now we are having IL. So if I follow the same steps and if I simplify it, then we'll be getting IL is equal to again Vs into under root C by L into sine of omega 0 t. In the previous case, we got this expression for current I, na? Now this is IL. But whether IL and IT both are same or not, you can check IL and IT both are same, na? So therefore, what is IT? So therefore, IT is equal to again IL is equal to same expression Vs under root C by L into sine of omega 0 t. Means again we are getting the current in the circuit is sinusoidal only. Same thing. Okay, now from this VC we can write again whatever we have written in the previous case. VC means whatever the discussion we had for the low value of REL, the same expression, same discussion will be applicable in this case also. In this case also. Is this clear? So we can write VC, that is the voltage across capacitor, is equal to Vs into 1 minus cos of omega 0 into T. Omega 0 into T. Right? You can check. You can write the VC is equal to 1 by C integration over 0 to T IL into dt or IT into dt, anything you can write. Okay, so from that, after putting the expressions, okay, you'll be getting VC. After simplifying it, we'll be getting VC. You can check this expression of VC and whatever the expression we wrote here, both are same, right? You'll be getting the same expression only, right? So again, the same discussion we can do. Okay, the thing is for low value of REL, we need to connect it in series. For high value of REL, we need to connect it in parallel with the capacitor. Okay, but generally this circuit is not preferred because we are having the voltage commutation and current commutation circuits. Those are the most power, we can say the most popular circuits. Okay, this circuit is having the drawback like this is for only resistive type of load. Okay, right? So that's why we are not generally using these circuits. Okay, we'll take a break here. We start at 7:25. Okay, 7:25 will start. I don't think this derivation, okay, they can ask for the conventional type exam. No, I don't think so, right? Simply go through it because the same thing we are going to discuss again in the second, voltage and the current commutation, because there also we are having the DC supply and inductor and capacitor type thing, right? So yes, here capacitor will discharge through REL. Okay, so here your circuit turn off time, yes, it will be finite, you can say. Okay, so why natural commutation is not applicable for DC? You can natural commutation, you can check here for DC. In order to turn off the SCR, what we are doing, we have connected the external elements, the inductor and capacitor. If you want to suppose if the inductor and capacitor is not connected in this circuit, suppose this is the circuit we are having, and if I yes, inductor and capacitor are not connected, then is there any possibility of getting the zero current in the circuit? No, you cannot get the zero current. So that's why whatever the requirements are there now for commutation, those requirements cannot be used here, cannot be reached here, right? So that's why we need to go for the force commutation. But whereas for AC, the due to the nature of the supply, yes, due to the nature of the supply, yes, current flowing through the thyristor becoming zero, and as well as the reverse voltage is maintained. TQ is, that is a device turn off time that will be specified by the manufacturer. TC, you can say TC, circuit turn off time. Okay, you can ask here. Okay, so that TC will depend on, because you can check once capacitor charges in this circuit, once capacitor charges in this circuit to the 2 Vs, na, plus here minus here, it is like a 2 Vs. Once capacitor charges like this, capacitor is having the discharging path available here. Okay, so for that, yes, we need to write the expression for the discharging current of the capacitor. It is like a simple DC supply, R and C type of circuit we are having, right? So from this you can write the expression for the current flowing through the capacitor, that is I is equal to 2 Vs divided by REL into e to the power minus T by tau. Okay, and from that you can find the TC, right? Okay. Nitesh, do you want to speak something? So Mitri, do you want to ask something?
Hello, sir.
Yes, please.
Sir, I have doubt in natural computation.
In the natural computation. Yes.
Yes.
Okay. Yes.
Sir, here CR is on after giving the gate pulse, na sir?
Yeah. At t is equal to 0. That is omega t is 0. Huh?
Sir, here IT, sir, in waveform, IT is starting from 0.
Yes.
Sir, why it here gate signal is given? Sir, it will start not from 0.
What you are saying?
Sir, here gate signal is given. Sir,
Yeah.
sir, why IT is starting from 0?
Because as soon as gate signal is applied, our SR will turn on.
Yes, sir.
But
Sir,
if your gate signal is not maintained till that anode, that is SR current, reaches the latching current, na, then again SR will turn off.
okay, sir.
Right? As soon as you apply the gate signal, SR will definitely turn on. But if that gate current is not maintained till TP, TP means what? The instant at which the SR current becomes equal to latching current, na? We discussed the numericals.
Yes, sir.
Right? So
Okay.
definitely SR will turn on at 0, omega t 0. Right?
Okay, sir.
Okay.
Sir, in load computation, sir,
Huh.
sir, T is equal to 0, sir, capacitor is open
Open
circuit.
circuit. Yes. So
Sir,
capacitor will short circuit, not open circuit.
sir, how, sir?
Actually, it is having a relation with your transient response.
Sir,
You can check na, capacitor is the element which opposes a sudden change in the voltage. So before t is equal to 0, the current flowing through the capacitor voltage was 0, na, because it was like our thyristor was in off state.
yes, sir.
So that's why there was no path for the charging of the capacitor.
That's
So
why open
capacitor voltage was 0 for t less than 0, right?
okay, sir.
So that's why if capacitor voltage is 0 for t less than 0, so at t is equal to 0, as soon as this switch is turned on, na,
Yes, sir.
our capacitor will oppose the change in the voltage. Means what? Capacitor will try to maintain the same 0 volt, na?
Yeah,
So
yes,
if
sir.
capacitor try to maintain the same 0 volt, the meaning is capacitor will act as a short circuit, because in short circuit the voltage is 0.
So capacitor act as short circuit.
Yes, capacitor acts as short circuit. The same thing we have written here, na, shown here.
Okay, okay, sir.
Right?
Thank you.
Inductor acts as open circuit.
Yes, sir.
Okay, okay. So we'll take a break here. We'll discuss other doubts after the break, right? Okay. So now we are going to discuss the voltage commutation, right? The second type of the force commutation, that is the voltage commutation. Here in the voltage commutation, the SCR is turned off due to the high reverse voltage maintained across it. Okay, so that's why it is known as the voltage commutation. SCR is turned off due to the high reverse voltage across it. Okay, so that's why it is a voltage commutation. Whereas the next we will be discussing about the current commutation. In that case, the SCR turns off due to the when the current flowing through the SCR becomes zero. Okay, means due to the current becoming zero, at that instant the SCR turns off. That's why it is a current commutation. We'll discuss it. What is the difference between the two? So here you will understand, in the voltage commutation, actually the high reverse voltage will be maintained across the SCR. So here it is a circuit diagram for the voltage commutation. This is a supply voltage Vs. Here it is a capacitor C. The voltage across capacitor is said to be positive if upper plate is higher potential and lower plate is at lesser potential. Main thyristor is T1. TA is the auxiliary thyristor. Means in order to turn off the main thyristor, we are using the one more thyristor, that is the auxiliary thyristor. Next we are having the inductor L, diode D, and here it is the RC, right? And here it is a switch S. Freewheeling diode which is connected across the load. Load is a RLE, and here we have considered the load is highly inductive. Load is highly inductive. So let me write, load is highly inductive. Highly inductive. So if the load is highly inductive, the meaning is the load consists of high value of inductor. As we know, the inductor is having a tendency that it opposes the change in the current, right? So if the load is a highly inductive, the meaning is if the load consists of very high value of inductor, then we'll be getting the constant load current. We'll be getting a constant load current, right? So always keep it in mind in power electronics. As and when if I say the highly inductive load, then it will be a constant load current only, right? In the case of rectifier also, we are going to discuss the highly inductive load, right? Next, so that's why you can check, as the load is highly inductive, so I0 we are having, it is a constant current. This is the I0, which is a constant current, right? Next, so in order to turn off the, means you can check, we are having the supply voltage Vs, main thyristor T1, and here it is a load. Apart from these three elements, whatever the other elements here we have connected, all these are the commutating elements, right? Means these are the external elements we have connected in order to turn off the SCR, But whereas in the natural commutation, yes, the external elements are not required, right? Next, so now let us discuss the waveforms. Here IZ1, that is the gate pulse through the main thyristor, that is the thyristor T1. Let me write it as IZ1. This is the gate pulse to the thyristor T1. Gate pulse to the thyristor T1. Okay. Yeah. Next, IZA is the gate pulse to the auxiliary thyristor. This is the IZA, that is the gate pulse to the auxiliary thyristor. Next one is the load current I0. IT1, thyristor T1 current. IC, capacitor current. IT1 will be like this. This is your IT1. IT1, that is the thyristor T1 current. Okay. IC, that is the capacitor current. This is the IT1. Let me write it as, right, IT1. IC, that is a capacitor current. VC, voltage across capacitor. VT1, voltage across thyristor T1, and V0, voltage across the load, right? V0 is the voltage across load. Okay. Now let us discuss the circuit operation, right? How these waveforms are like this, and those things we are going to discuss now. So initially it is like a, for t less than 0, okay, the thyristor T1 was in a off state. For t less than 0, thyristor T1 was in a off state, and this switch yes was in a on state. Okay, so for t less than 0, thyristor was in a off state, auxiliary thyristor also was in a off state, and switch was in a on state. Switch yes was in a on state. So let me write, for t less than 0, switch yes was in a on state, main thyristor T1 and auxiliary thyristor TA both are in a off state. Both are in a off state. So you can check in this circuit, if the main switch is in a on state and these two thyristors are in a off state. Okay, so how is the circuit operation? It is like current will be flowing from Vs capacitor, this RC, and back to the Vs. In this loop the current will be flowing. Okay, current will not flow from source towards the load because main thyristor T1 is in a off state. Current will not flow through the auxiliary thyristor because auxiliary thyristor will be in the is in a off state. Okay, diode D will not allow the current here. Okay, so current will not flow from source towards the load at all. So in order to maintain the same current, it is like, yes, current was flowing through the freewheeling diode only. Okay, current was flowing through the freewheeling diode only, means it is like in our load inductor has already stored the energy and a load inductor is releasing the energy. Now let me tell you, in this specific commutation circuit, we are not interested actually in the waveform of V0. What we are interested in the waveform of VT1, VC and IC and the current IT1, because this is a commutation technique, na? Right? Same circuit again we are going to discuss in the DC to DC converter. In that the same circuit is renamed as, yes, it is a voltage commutated chopper circuit type. Okay, voltage commutated DC to DC converter or voltage commutated chopper circuit. Right now, so here as I said, switch S is in a on state, so it is like capacitor go on charging. So it is like for t less than 0 only, capacitor was charging, and as time t approaches the 0 minus, it is like our capacitor will be charged to the voltage of Vs volt. Right? So let me write it as, at t is equal to 0 minus, at t is equal to 0 minus, right? It is like a capacitor voltage is equal to Vs only. And how the capacitor is charged? The upper plate positive, lower plate negative, right? Means here it is a plus, here it is minus. This capacitor voltage is equal to Vs now. This capacitor voltage is equal to Vs, means here it is plus, here it is minus. This voltage is now Vs. Is this clear? So what is the function of this switch? Is actually the function of switch is to initially charge the capacitor to the voltage of supply voltage. That's it. Okay. For this purpose, this capacitor C is used. Okay. Next. Now, at t is equal to 0 minus, capacitor is charged. Means before t is equal to 0, the capacitor voltage is like it is a Vs only. Capacitor voltage is equal to Vs. So let me write, this voltage is equal to Vs. This voltage is equal to Vs. Right? Now let us discuss for at t is equal to 0 or for t greater than 0, what will happen? Okay. So suppose now we have opened this switch. We have opened this switch, right? And at t is equal to 0, if you check the waveform, at t is equal to 0, at t is equal to 0, we have applied the gate pulse. At t is equal to 0, we have applied the gate pulse to the thyristor T1. We have applied the gate pulse to the thyristor T1. So what will happen? At t is equal to 0, as the gate pulse is applied to the thyristor T1, so our thyristor T1 will turn on. Once the thyristor T1 turns on, the current will flow. Yes, current will be flowing like Vs, T1, load, and again back to the Vs. In this loop, the current will flow. That is the outer loop. At the same time, our capacitor go on discharging. Our capacitor go on discharging through C, T1, inductor, diode D, and again back to the C. Means in this loop, the capacitor discharges. Are you getting the point? Means at t is equal to 0, thyristor T1 is turned on. As soon as thyristor T1 turns on, what will happen? Yes, we are having the two loops in the active state. First loop is outer loop. That is the current is flowing from Vs, thyristor T1, load, and again back to the Vs. In this loop, the current is flowing. And at the same time, the capacitor also discharges through the main thyristor T1, L, D, diode D also in the on state, no, right? Because diode D will be in the forward bias mode now. Okay. So that's why capacitor will go on discharging into this loop. Capacitor discharges into this loop. Are you getting the point? Auxiliary thyristor is still in the off state only. capacitor is discharging through main thyristor T1, inductor L, diode D, and again back to the capacitor C. When the current flows from Vs T1 load, this freewheeling diode will be like in the off state. Freewheeling diode will be in the off state. So now let us discuss the, can we draw the equivalent circuit during this mode 1? You can check mode 1 means what? T1 is in an on state, diode D is in an on state. The same thing we discussed, the diode D is in an on state, T1 is also in an on state, na? Right? Why the diode D is on state? Because voltage across capacitor will be like a forward voltage for the diode D. So that's why our diode D will be in the conduction mode. And at the same time, gate pulse applied to thyristor T1. So thyristor T1 is also in the on state. So for the mode 1, let us draw the equivalent circuit, right? How it will be for mode 1? For mode 1. Yes, equivalent circuit we can draw. Main thyristor T1 is in a on state, right? Here it is a supply voltage Vs. Okay, here it is a capacitor. Capacitor is voltage is like plus here minus here. Capacitor is charged to the voltage of Vs volt. Na? Next, auxiliary thyristor is in a off state. Diode D is in a on state. Inductor, and here it is a, yes, we're having this type of circuit. Here freewheeling diode will be in a off state, and here we're having the load R, L, and E. So this type of circuit will be having for mode 1. This voltage is Vs. This is a Vs capacitor C. This is thyristor T1. Current flowing through thyristor T1 is IT1. This is auxiliary thyristor TA. Diode D, and here it is a inductor L. Right? Capacitor C current, you can check IC direction we have not mentioned, right? So let first of all, let us indicate that IC positive current direction, right? So IC will be positive if plus if the direction is in the upward direction. Okay, consider IC here, capacitor current. Okay, and that will be positive if current is in an upward direction. So here we are having the IC. So this circuit we are having here. What is happening? Capacitor is discharging through the main thyristor T1, inductor, and the diode D. At the same time, current is flowing from source towards the load through the main thyristor T1. Okay, through the main thyristor T1. So this is R, L, and E. This voltage we are having is a V0, and this current is a I0. Now for this circuit, if you check, can we say that V0 is equal to Vs only? Because whatever the polarity at the positive plate will appear at this positive terminal of the V0, and whatever the negative plate potential here, the same will appear at the negative terminal of the V0. So can we say that V0 is equal to Vs? Because between the V0 and Vs, we have only short circuited thyristor T1. Na? So that's why here V0, you can apply KVL to the outer loop E1. It is a plus Vs minus V0 is equal to 0. So that's why V0 is equal to Vs. Okay, so V0 is equal to Vs will be getting. That is the load voltage. Next, now as capacitor is discharging here, right? Capacitor is discharging. So can we apply KVL to this loop only so that we can get the expression for the IC? Are you getting the point? What I am saying? Okay. So here capacitor is discharging through this loop. So we need to apply the KVL to this loop in order to get the expression of the IC. Right? Now, yes, let me redraw this network. Let me redraw this only this loop, and this inner loop I am redrawing such that we are having the passive capacitor C. Initial voltage across capacitor is Vs, and here it is the inductor L and a diode D, which is in a on state. Right? So we are having the elements like, yes, let me draw the inner loop only. So capacitor C, which is initially charged to the voltage of Vs volt. Here it is a thyristor T1. Next, here it is a diode D, inductor, and yes, this is the IC. Okay, this is the IC. Now, can we redraw this network? Either we are having the two cases, we are having the two possibilities. First is we can directly apply KVL to this loop, and while taking the Laplace transform, okay, we need to use the non-zero initial condition. Okay, initial condition non-zero. One case is there na in the Laplace properties. That case we need to apply here, or in the time domain itself, we need to add the initial voltage across the capacitor and the passive element separate. Okay, and then we can apply the KVL, and then we can take the Laplace transform with a zero initial condition, because in the Laplace transform, if you check, we're having the zero initial condition property, that is the different, that is the normal Laplace transform, and second one is we're having the with a non-zero initial condition property, right? So I am saying that either we can apply KVL to this loop directly, okay, KVL to this loop directly, and while taking the Laplace transform, okay, we need to use that non-zero initial condition property, or yes, we can add this non-zero initial voltage of the capacitor in the time domain itself, because Laplace means what? Laplace is converting your time domain to the S domain, na? Right? The thing is time domain to the S domain. So if we consider this initial, if we add this initial voltage in the time domain itself, then we need not to go for non-zero initial condition property of the Laplace. Okay, so what I am doing, the same circuit I am redrawing as, yes, it is like we're having the initial voltage, that is a Vs of the capacitor. I have represented this as a with a voltage source, so please be careful, because this is the initial voltage. Next, I am representing the capacitor here, this capacitor and this voltage, right? This voltage is like initial voltage across the capacitor. This capacitor C is nothing but your passive capacitor, right? Next, same thing, diode is here as it is, inductor is here as it is, and here we are having the thyristor T1. Okay, if I redraw this network, this circuit as this one, then while taking the Laplace transform, we need not to use the non-zero initial condition property. Are you getting the point, right? So now, can we apply KVL to this loop? This is IC, na? KVL to this loop. If we apply KVL, yes, KVL to loop, so we can get it as plus Vs minus L into DIC by dt, na? Because here actual current flowing is your IC, same current is flowing here, na? So that's why it is a DIC by dt, capacity discharging in this loop. So that's why it is a DIC by dt minus 1 by C integration of IC into dt is equal to 0. Now we can write therefore Vs is equal to L into DIC by dt plus 1 by C integration of IC into dt. Further, you can check now in the previous case also, that is the load commutation, whether we got this same expression after neglecting for the low value of RL, after neglecting the voltage across RL. Okay, we got this same expression, na? Yes or no? And the same thing, whether we if we take the Laplace transform, what the final expression we got? The expression for the current. So in this way, in this case also, if we take the Laplace transform on both sides, we'll be getting it as Vs by S is equal to L into IC of S plus 1 by Cs into IC of S. So it is equal to again L plus 1 by Cs into IC of S and Vs by S. The same steps we followed there. Okay, so no, I am directly skipping those steps. So what is the final expression? Because after this, what we will be doing? We'll be taking the cross multiplication, right? It is a LCS plus 1 divided by CS. Yes, yes, will get cancelled. Next, make the coefficient of that S to be equal to 1, right? We need to write in this way. Okay, so therefore we can write it as LS should be there, right? LS should be there. Is this clear? Yes, LS should be there because Laplace of differentiation is yes, na? So that's why it is LS. So that will be like LC into S square plus 1 divided by CS. Take the LC common, make the coefficient of S square to be equal to 1. Same steps. So after that, at the end, we'll be getting IC is equal to Vs into under root C by L into sine of omega 0 t. You can check where omega 0 is, 1 by root LC, na? You can check the same expression we got in the previous case also. Here we're having, yes, for RLC, low value of RL, if you check, Yes, this expression after taking the Laplace, there's Vs by S minus. Only thing is, if I shift these two terms to the right hand side, we'll be getting whatever the expression we have written na just now. So at the end, we'll be getting current in the circuit na. It is Vs under root C by L sin of omega 0 t. So that's why here also we are getting the current in the circuit, that is a IC is Vs under root C by L into sin of omega 0 t, where omega 0 is 1 by root LC. Omega 0 is 1 by root LC. Means the nature of the current IC is sinusoidal. Nature of the current IC is sinusoidal. Is this clear? Now, if IC is sinusoidal, what about the VC? VC will be your cosinusoidal, na? If IC is sinusoidal, VC will be cosinusoidal. Okay, so you can check the IC waveform here. You can check the IC waveform during mode 1. During mode 1, IC waveform is, it is like this, sinusoidal. And how is the waveform of VC? VC is a cosinusoidal. VC should be, yes, it is like this. It is a cosinusoidal waveform. Cosinusoidal waveform. Okay, means the meaning is what is happening in the inner loop actually? What is happening in the inner loop? The capacitor is discharging and again charging to the reverse polarity. I'm saying capacitor discharges and again charges to the reverse polarity. So you can check capacitor initially voltage was Vs, that is upper plate positive, lower plate negative. That voltage is plus Vs na. So we considered that voltage is plus Vs. As soon as this thyristor T1 turns on, our capacitor starts discharging through the T1, L, D, and again back to the C. So capacitor discharges and again charges to the reverse polarity. Reverse polarity means what? It is like a lower plate positive, upper plate negative. Lower plate positive, upper plate negative. So you can check VC waveform. Capacitor voltage is decreasing. So it is like capacitor is discharging and again charges to the reverse polarity. Charges to the reverse polarity. So voltage across capacitor changing from plus Vs to the minus Vs, plus Vs to the minus Vs. Is this clear? So capacitor discharges and again charges to the reverse polarity. So what about the IC? IC is the sinusoidal here. IC is your sinusoidal. Is this clear? Right? So once capacitor discharges and charges to the reverse polarity means you can check. Once capacitor here in this loop, yes, in this loop we are having, yeah, this loop, inner loop na. This is a T1 we are having. So once capacitor discharges and charges to the reverse polarity means the reverse polarity voltage, if you check across the capacitor, it is like plus here and minus here. And this voltage is equal to Vs only. Capacitor has discharged and again charged to the reverse polarity. Na? So that's why it is plus here, minus here. So now this is plus, this is minus. So can we say that it is like a higher potential will appear at the, this is for the cathode of a diode now. This is the anode of a diode. Yes or no? You can check the circuit. Okay. So it is like when capacitor discharges and charges to the reverse polarity, it is like our diode. Capacitor discharges and charges to the reverse polarity. Our diode D will be in the reverse bias mode. So diode D will turn off. Diode D turns off. Diode D turns off. So what will happen? Our capacitor will not discharge through this loop na? Because discharging path is, because diode D will not allow the reverse current. Next, capacitor will try to discharge through the auxiliary thyristor, but whether we have applied the gate pulse to the auxiliary thyristor yet? No. Auxiliary thyristor is in off state only. So that's why discharging path is not available for the capacitor. So capacitor will hold the same voltage, that is the minus Vs. That is the minus Vs. You can check here. After capacitor discharges and charges to the reverse polarity, you can check during the mode 2 till we apply the gate signal to the auxiliary thyristor, capacitor voltage will be equal to minus Vs only, because discharging path is not available for the capacitor. Discharging path is not available. Is this clear? Means during mode 1 what has happened? Capacitor has discharged and charged to the reverse polarity, right? IC is sinusoidal, VC is cosinusoidal. Now let us check what is the IT1. What will be the waveform for the IT1? IT1 means what? IT1 is like your IC plus I0. Na? If this current is I0, if this current is I0, can we say that here current is also I0? You can check the same current is coming here na? And same current is flowing here. Same current will be flowing through the supply voltage. So can we say that if this current is I0, therefore supply current is also I0? So what is the current flowing through thyristor T1? Thyristor T1 current is equal to your I0 plus IC. So IT1 is equal to I0 plus IC, right? I0 plus IC. Okay, so let me write IT1 is equal to I0 plus IC. We are discussing only mode 1. So IT1 is equal to I0 plus IC. I0 plus IC. This is IT1. Right? This is the IT1. Okay. It is a I0 plus IC. Now you can check the IT1 waveform even. IT1 waveform. IC is like this. IT1 is I0 plus IC na? At t is equal to 0. At t is equal to 0, what is IC? IC is 0. At t is equal to 0, IC is 0. So what is the IT1? IC plus I0. So IC 0 means IT1 is equal to only I0. So that's why this will be like your I0 only. After that, as IC increases, IC plus I0 value, that addition increases na. So addition of this I0 plus this IC will be like this only. Will be like this. You can add this I0 waveform and this IC waveform during the mode 1 interval. I am saying. Okay. So you'll be getting IT1 is nothing but I0 plus this. That is why this type of pulse will be getting. Is this clear? Right? So therefore here you can check what is the peak value of current flowing through thyristor T1 now. I0 plus what is the peak value of capacitor current? Peak value of capacitor current you can check here. Vs under root C by L na. This is the peak value of capacitor current. Let me write it as IC peak. IC peak. That is a peak value of capacitor current. Right? IC peak. Let me use the small letter. IC peak. Right? So this is the IC peak. Right? It is a peak capacitor current. Peak capacitor current. Peak capacitor current. Don't lose the concentration, right? Be focused. This is the only starting of the power electronics. Okay, so as long as this course is considered, you can check even in the GATE syllabus. They have mentioned, they have given or the power electronics at the very last. Na? Why? Because in order to understand the power electronics, yes, you need to be perfect. You need to understand. You need to be familiar with concepts of all other subjects like a network, like your electromagnetics, because L and C are related to your electromagnetics, right? For the network, we are having the KCL, KVL, and those things. Okay, so that's why they have specifically kept the power electronics at the last. Okay, in the syllabus even. Network not done. Yeah, I know, but try to understand only whatever I'm explaining here, right? So IT1 is I0 plus IC we are having. So IT1, if you check, it is a addition of these two waveforms. So that's why it is this type of waveform we're getting. Capacitor voltages, capacitor discharges and charges to the reverse polarity. What is the VT1? Voltage across thyristor T1. During mode 1, thyristor T1 is in on state now. So that's why VT1 will be 0. So from here to here, you can check mode 1. VT1 is 0 only. What about the V0? We have written V0 is equal to Vs. So during mode 1, V0 is equal to Vs only. This is a Vs, right? V0 is equal to Vs. Next, now let us check for the mode 2. During the mode 2, what will happen? Okay, so during the mode 2, if you check, actually we have not applied the gate signal to the auxiliary thyristor. Na? We are applying the gate signal to the mode to the auxiliary thyristor at the start of mode 3. Okay, so during the mode 2, what is happening? Yes, it is like a auxiliary thyristor is in an off state only. Capacitor has charged to the reverse voltage only. Discharging path is not available for the capacitor. Okay, so during the mode 2, if you check, this diode will be in the reverse bias mode. Discharging path is not available for the capacitor. So capacitor will hold the same voltage. The only thing is thyristor T1 is in an on state. Current is flowing from Vs, T1 load and again back to the Vs. Only in this loop the current will be flowing. So during mode 2, let me draw the equivalent circuit. During mode 2, if you draw the circuit, it will be like this. Where I'm going to supply voltage Vs, right? So here thyristor T1 is still in the on state only. Load is RLE. This voltage is V0. This current is I0. Freewheeling diode will be in the off state. Capacitor has charged to the reverse polarity, na? So that's why capacitor voltage will be like minus here plus here. This is a Vs, because during mode 1 capacitor discharge and charge to the reverse polarity. Auxiliary thyristor off state. Diode D will fill the reverse voltage. Diode D will be in the off state. And here it is an inductor, right? So this is the inductor L, diode D, auxiliary thyristor. This is the IC. This is a T1. This current is IT1, right? So this type of circuit we are having during the mode 2. So capacitor is not discharging because discharging path is not available. So what is the IC? Definitely IC is equal to 0 ampere because discharging path is not available for the capacitor. Next, now if capacitor is not discharging, so therefore inner loop current will be 0 only. So only thing is we'll be having the current that will be flowing from source towards the load through the main thyristor T1. So can we say that? But load is a highly inductive now. So load current is our constant current. So I0 is equal to I0 only. So can we say that during mode 2, IT1 is equal to your I0 only, because the current is flowing from source towards the load is through the thyristor T1 na? That is the outer loop current is flowing. So that's why IT1 will be equal to I0, which is equal to capital I0. Okay. IT1 is equal to I0, which is equal to capital I0, right? This is your IT1. What about the VC? VC is equal to minus Vs because capacitor charged to the reverse polarity na? So that's why VC is equal to minus Vs. Okay. IC 0, VC minus Vs, IT1 is I0. What about the V0? You can apply KVL to the outer loop because current is flowing in the outer loop na? If you apply KVL to the outer loop, plus Vs minus V0 is equal to 0. Plus Vs minus V0 is equal to 0. So therefore V0 is equal to Vs, right? Load voltage is equal to source voltage, same as that of the supply voltage. Supply voltage is DC, so therefore you will be getting V0 is a constant voltage, right? Next, what about the VT1? VT1 is this voltage. Thyristor T1 is in on state na, so VT1 will be 0. VT1 is equal to 0 volt, right? VT1 is 0 volt. So let us check the mode 2 waveforms. Mode 2 waveforms. IC 0. Yes, here you can check during mode 2. First thing is IT1 is I0 only. IT1 is I0, right? Next, I0 is a capital I0, that is a load current. Okay, IT1 and I0 both are same. IC is 0. You can check IC is 0 here, mode 2, IC 0. What about the VC? VC is minus Vs only because discharging path is not available for the capacitor. Okay, VT1 is 0 because thyristor T1 is in a on state. And what about the V0? V0 is equal to Vs, na? Same as that of the Vs. So V0 is equal to Vs. This is during the mode 2. During the mode 2. Now, mode 3, let us discuss. At the start of the mode 3, we are applying the gate signal to the auxiliary thyristor. Na? We are applying the gate signal to the auxiliary thyristor. So you can check in the circuit. Capacitor has charged to the voltage like minus here plus here. Na? This upper plate negative, lower plate positive. Capacitor voltage is Vs. So when the gate pulse is applied to the auxiliary thyristor will turn on immediately. So as soon as auxiliary thyristor turns on, what will happen to the main thyristor T1? You can check. As soon as auxiliary thyristor turns on, this capacitor will try to discharge. This capacitor will try to discharge in opposition to that of the main thyristor T1. Please try to understand. This is very important, right? So here, as soon as thyristor TA turns on, this capacitor will try to discharge in this loop. But if you check in this loop, we are having a capacitor which is charged to the voltage of Vs volt. And in this loop, we don't have any other element now to restrict, to limit the discharging current of the capacitor. So therefore, you can imagine if the capacitor voltage is like plus here, minus here, and the magnitude of that capacitor voltage is Vs volt, and in the discharging path, we don't have any resistor, we don't have any inductor. So what will happen? As soon as this thyristor TA turns on, suddenly very high current will flow. Suddenly very high current will flow in opposite direction for the thyristor T1. Means suddenly very high reverse current will flow for the thyristor T1. So due to that, what will happen? You can check as soon as thyristor TA turns on, our thyristor T1 turns off. Why? Because this capacitor will try to discharge through this loop, and in this discharging loop only capacitor is there, right? Any any other element that is to limit the capacitor discharging current is not available, is not present. So that's why what will happen, suddenly the capacitor will try to circulate a very high current. If that very high current is circulated, what about the resultant current in the main thyristor? It is like in the main thyristor, one current is that is flowing from source towards the load, that is a I0. Second current is a discharging current of the capacitor. But as I said, the discharging current of the capacitor is very high. So what about the resultant current? The resultant current will be your reverse current only. So that's why immediately the thyristor T1 current IT1 becomes 0. As soon as TA turns on, your thyristor T1 turns off. So you can check IT1 waveform. Here you can check IT1 is suddenly becoming 0 here. Why the IT1 has suddenly changed from I0 to the 0 value? Because this capacitor will try to discharge in this loop here. And in this loop, there is we don't have any other element to limit the discharging current of the capacitor, right? So here capacitor is turned off due to high reverse voltage appearing across it now. So that's why it is a voltage commutation. That's why it is a voltage commutation. Is this clear? So as soon as TA turns on, the capacitor voltage will appear as a reverse voltage for the thyristor T1. So thyristor is turned on, thyristor is turned off, thyristor is turned off due to the high reverse voltage. So that's why it is a voltage commutation. Is this clear? That's why it is a voltage commutation. So that's why thyristor T1 current becomes 0 suddenly. Now when the thyristor T1 current becomes 0, please try to understand. When thyristor T1 current becomes 0 means thyristor T1 will turn off. So when thyristor T1 turn off, then what will happen? This capacitor will try to discharge. This capacitor will try to discharge through a C, TA, load, and again Vs, and back to the C. In this loop, the capacitor go on discharging. I'm repeating. As soon as thyristor T1 turns off, our capacitor will discharge through auxiliary thyristor, load, supply voltage, and again back to the C. In this loop, the capacitor will discharge. But if you check here, when capacitor discharges through the auxiliary thyristor, when capacitor discharges through the auxiliary thyristor and a load, when capacitor discharges through the auxiliary thyristor and the load, what is the current that will be flowing through the capacitor? That will be equal to your load current now. But load is highly inductive. So that's why load current is constant. So can we say that if the load current is constant, therefore capacitor current is also constant? But you can check when capacitor discharges now, what is the direction of current flowing through the capacitor? In the capacitor branch, that current will be in the downward direction. And we considered a capacitor current positive means IC upward. But actually capacitor when capacitor is discharging now, so here the current flowing through the capacitor is in downward direction. So therefore IC should be equal to minus I0 only. IC is equal to minus I0 only. You can check the waveform, right? Now let me draw the equivalent circuit during the mode 3. Let me draw the equivalent circuit during the mode 3. Whether the surrounding noise is disturbing. No, na, right? Yes, yes, sir, a bit. No. Okay. Yes, yeah. So now, yeah, let me draw the equivalent circuit during the mode 3. I will first draw the equivalent circuit, and again I will explain the operation, right? For the mode 3 specifically. Mode 3. What is happening in the mode 3? First of all, auxiliary thyristor turns on. So when auxiliary thyristor turns on, immediately thyristor T1 turns off, right? So T1 will turn off. Capacitor was like, here it is a minus, here it is plus, this voltage was Vs, capacitor voltage, okay, is equal to Vc. This capacitor will discharge through the auxiliary thyristor, okay, here it is, and at this side we're having the load. Is this clear? And here we are having the diode D, which is in a reverse bias mode, right? And here it is an inductor. This is inductor. Next, now you can check here during the mode 3, what is happening? At the start of the mode 3, the gate pulse is applied to the auxiliary thyristor. As soon as the gate pulse is applied to the auxiliary thyristor, our capacitor will try to discharge here. Okay. So when capacitor try to discharge through the main thyristor T1, in this discharging path, yes, we have only capacitor, and that too charged to the voltage of Vs volt. So that's why to limit the discharging current, we don't have any other element present. So that's why suddenly very high reverse current will flow, and that's why resultant current flow thyristor T1 suddenly fall to the 0 value. Okay, so this is the VT1, and immediately our thyristor T1 will turn off. Once the T1 turns off, then what will happen? Our capacitor will discharge through this loop. This is the R, L, E. This is the V0, and this is the I0, which is equal to capital I0, right? So you can check capacitor will discharge through this loop. Now it is like capacitor will discharge like C, TA, load, Vs, and again back to the C. In this loop, the capacitor discharge. But when the capacitor discharges in this loop, what is the IC? Actually, we consider the positive value of IC is nothing but this type of, okay, this is like your positive current IC. But actually when capacitor discharges, the IC is flowing in the downward direction. So can we say that IC is equal to minus I0? Yes or no, right? IC is equal to minus I0. IC is equal to minus I0, right? So here IC is minus I0. Capacitor discharges, capacitor C